None of those is an Airbus or a Boeing. So if you want to fly from LA to Sydney or to Australia somewhere, New Zealand, you don't take a regional jet. That's not the appropriate approach. So if we want to write a bold story, to think about kilometer scale modeling, the key thing is to keep in mind always the needs of the global society. We have to get mired down in the physics. We have to get mired down in the research questions and so on. But there are a lot of places and ways for us to do that. Conferences all over the place where that happens. This particular gathering, I think, is not just about that. It's about something bigger, something broader, something at a higher level of thinking. So, we really have to take a new approach. We've got a lot of Embraers and Canada Airjets out there and so on right now. They're doing amazing things. We don't really have an Airbus. And so I think what we ought to realize is that whatever we're going to be doing is going to feel uncomfortable, and it better feel uncomfortable, because otherwise it's not probably what we need. And so dragging us out of our comfort zone, I think, is terribly important. So what would be our vision? Well, I just wrote one this morning for the heck of it. A vision isn't a goal, it's a vision. Our vision would be that global society makes decisions regarding our changing climate globally using statistically reliable, minimally biased, fine-scale information available to all that's delivered in ways that support practical decision-making across the entire range of users involved. Now, not all of this is our responsibility to do, but it's our responsibility to connect to stakeholders and so on and so forth. I don't know if this is the right vision or not, but I think we need a vision. We need something that really is a globally empowering vision, a globally engaging vision that brings folks together. And so, remember this enabler I mentioned, the creation of this specialized computer. It's not a single purpose machine that would, or environment, not really even a machine, but it's an environment, virtual environments that allow us to do things that we're not able to do now. But if we're going to be trying to run a lot of regional jets, around it, I think we're not gonna get to where we need to get to, because we're doing that today. So I think the danger for us today and tomorrow is we don't want to spend all of our times in the weeds on research questions and things that are already being done. They're very important, but there are a lot of venues to do that. We've got some of the best minds on the entire planet here to think about, as a global community, how do we move this forward? And I think Bjorn wrote an email message that Maria shared yesterday. He said, really, let's try to focus on these bigger picture issues. And that's really important. Destiny is doing great things, Eve and so on. But we don't have this sort of globalized community to do the things that we're talking about here. So we should take the unique time that we have here to together to look through the lens of this global responsibility that we all have, not to debate this physics package or that, but to think about how we mobilize the community administratively and scientifically to achieve that proposition and bring others together. That would be my hope. And think about the story we want to write and the headlines that would be written 10 or 15, 20 years from now because of the work that we will be doing as a global community that we can't even envision. But just think of what that will mean for different communities, for the insurance sector, for the financial markets, and so on. We can't even begin to envision that. So those are the headlines I'd love to figure out how we write. I think we can write some headlines now, but these other headlines are yet to come. So I woke up in the middle of the night, started thinking about all this stuff. I haven't had a chance to share it with the planning committee. They may start throwing heavy objects at me. I hope not. But let me invite them first to make some comments on this. And because we talked about this at dinner last night, not specifically what I've been showing you here, but I try to put it together and package it in a way that I think would be really accessible and something that would resonate in terms of writing our story. So Dan, do you want to start? Is there anything you'd like to share? I think the mics are live here. So please, and other folks on the planning committee or the Nucleus team, please do share your thoughts.
Yeah, no, it's on. I'll just endorse that. I think it is important, as we were talking about how we engage stakeholders, is I'll remind people that those of us who are in the U.S., the U.S. science enterprise largely started at the end of the Second World War when Vannevar Bush wrote a memo to President Roosevelt. And he reminded the president and others that there were 3 reasons why the federal government should be in the business of funding science. Making scientists famous was not on the list. The 3 things that were there were national security, economic competitiveness. There was a great fear that the world might fall back into the continuation of the Great Depression at the end of the Second World War as people tried to rebuild. And the third was public health, right? It was about helping people. That's why governments invest in what we do, is we're supposed to be stewards of the public trust to help the citizens of the planet. And I think what Kelvin is saying is right. That's how we have to think about this. What do we need to do in order to address these problems? And one of the things that becomes true at some point is you have to make some choices about what is good enough to move forward to a solution, because the perfect can be the enemy of the good in moving forward, right? So progress is progress. It might not be perfect progress, but it's progress. And I think it's important that we sort of think through that lens. So I heartily endorse what you said.
Great. Thanks, Dan. Any other thoughts or comments on this from anybody? Barb?
No, I agree with Dan, but as you were putting this up, I was reminded, and Jim Hack will remember this too. I've spent a lot of my time, my life, building up a community called computational scientists. And it seems what you're doing here is trying to build a new community out of a number of different communities. And I think that's important because you've got to get all the voices at the table to really make this a global community. And I think that's the biggest challenge is how are you going to build that? What kind of support system are you going to have? I mean, we go back to one of the reasons, you know, it was so difficult to do computational science. We didn't have like the APS or something like that. So you've got to take all of these disparate communities to bring them together and make them a family.
Yep.
So
Good
it is
point.
going to
Yeah.
be tough.
Thank you, Barb. Anything else? We'll shift gears here. Yeah, Chris?
Yeah, so I totally agree. We have a responsibility to our world of stakeholders to do a better job of bringing our science to them. I actually am not sure that is particularly a story that's related to better computation or even new information.
Yeah.
But regardless, in order to mobilize our own community just here in the US, and given that that community is already trying to address these questions in their own eyes, I think what we need to also do is like have a real scientific vision of what we can do with this that they cannot do or do better than what they're doing right now. And I think that has to be a compelling science vision. And when I reflected on this, you know, I thought about, okay, well, what are the most important issues in terms of the science of climate change? And two problems that have been difficult for a long time. One of them is the problem of cloud feedbacks and climate sensitivity. And the other one is of tipping points, of things that might go off the rails. And I think one of those that I find most concerning myself is ice sheet collapse in Antarctica. So I think we have to somehow relate what we're doing to advancing those fields. And it's not a perfect solution to either of those problems. And I think people could throw rocks at whether it's even a good solution, a good way of attacking either of those problems. But I think we don't have that kind of an effort. We're not going to bring the US science community along with us on this effort. So I think science vision, a grand challenge science vision is really important to making this project succeed.
That's a really great point, Chris. And in fact, you know, it really underscores the importance of the science community is in fact a stakeholder in this, and in some sense a driver as well, for sure. Yeah, please.
So, and again, as a non-climate scientist here, but maybe a representative of the general public, what I find super interesting is actually thinking about how do we make this data accessible to the broad public? How do we create data that is democratized in a way, not just that we upload a 5 petabyte ERA 5 data set to some publicly available
It's a hypothesis,
Right.
right? Yeah.
Yep. And we can only test it with having the models. That's right. I mean, a lot of dynamical downscaling like Francine and others do really give us a sense of that. But back to Tim Palmer's point about, the global scales, the interactions across scales really are only realizable with, and we're not talking about necessarily a uniform mesh. Obviously, there could be embedded patches and so on. But anyway, yeah, go ahead,
So
please.
I'm not a climate scientist, but as a sort of member of the public, boreal forests burning and putting out huge amounts of greenhouse gases or permafrost melting. But I think those kind of disasters are something that if they were visualizable, and we certainly have video of several huge fires recently, might be compelling.
Mhm. It's a really great point. And the thing is, it gets to this issue of humans and how far ahead we can look and really internalize. Some people think in terms of just, keeping groceries on the table. And then other people think about, well, my retirement or so on. And then other people think much longer term. And that's the real challenge, I think. How do we, given that these changes are being manifest now, how do we really make this real without thinking that, it's forever in the future? And that's why the one headline said, out to 2070, not out to 2150 or something like that. That's so far in the future and so unreliable that nobody looks at that. I mean, scientifically, it's very interesting, but in reality, it's a guess, right? So anyway, let's see. Go over Francina. Sorry, we'll go back.
Yeah, so I have 2 points. The first one is that, like, I teach about climate change and I give talks about climate change. And I always get to this point in my teaching or talks where I say we have 6 years to 1.5 degrees. Okay, so just this urgency that beyond 1.5, like, we are in unknown territory and the impacts are going to be dire. So I agree that as a scientist, I tend towards these kind of scientific issues, but right now we just don't have the luxury of time. We have to address this issue and provide data that can be usable by society. So that's my first point. We just don't have luxury of time. My second point is that we also have to think about what we're not going to do in this effort. And part of that is, we were mentioning yesterday, like mitigation, carbon. I think that is an issue that is well addressed in the CMIP effort, which is different from this effort. So biogeochemical cycles, all of this is not, in my opinion, what we should be doing. We should be focusing on, the variables that we need to make decisions at the short term, not at the longer term. So clearly identifying the timescales and what are the variables needed and what perhaps we're going to have to sacrifice to get to that endpoint.
Very well said, Francina. Thank you.
I'm Cliff. I'm a computer architect. So in some ways, from this perspective, I'm a tool builder. I helped build Anton machines, which did molecular dynamics for drug discovery, and Google's tensor processing units, which are AI accelerators. In building Anton, we had a pithy way of explaining it to lay people. We called it a computational microscope, a simulated engine that would allow you to resolve 1,000 times smaller than you could possibly do with standard experimental techniques. And a question I have for this room is, what's the equivalent layperson accessible description of what you want to do in this room? In spending 30 seconds on it, I came up with computational time machine. The problems that I think we're facing are, if we do nothing and we jump 30 years into the future, what does the world look like? If we do this intervention and we jump 30 years into the future, what does the world look like? And all of the why do you trust it stuff, which we focus on as scientists and engineers, is important in building a trustable time machine. But I think saying computational time machine, we believe this, we have the device. I think science fiction has made people believe some aspects of what scientists can do. And maybe we should play to that in saying, this is the capability we built as part of Kelvin's vision of the future. Because I think the world has to believe us. If you say Earth System Simulator or various other more egghead kinds of terms, people will just gloss over and not say, why should I, or go to, why should I believe that weird thing with the precise name?
I'm lonely up here. I'm going to go sit either at a table or have other folks join me, because this says planning committee and nucleus team, not Kelvin. So you all want to come up, or should I go sit in the? It's just a discussion, right? It's just so I don't feel like I should be sitting here. Should I go sit? Okay, I'm going to go sit, but I am going to hang on to a mic.
All right, well, I'm going to go ahead.
Go ahead.
I appreciated the comment earlier about the trouble matching historical observations with the GCMs, and I think that really points. I mean, if we think about sort of a 1970 or late 1960s inflection point in global warming, we've got that's like almost my whole life. We've got over 50 years of a pretty steady linear trend in climate change behind us. And a lot of the practical concerns that people have been talking about, like, civil engineering type terms, or, for EPRI's point of view, grid planning purposes, are, have a forward horizon of like 20, maybe 30 years. And so, really, really convincingly demonstrating that we can simulate the past really, really well seems like a super high priority, and moving, up the difficulty scale of things that we need to simulate that are important, for example, for the energy system, because that's the part I've been thinking about a lot, but I know for lots of other people as well. So, wind extremes, I mean, we can't even predict wind gusts tomorrow with our best NWP at this point particularly well. Hail, I don't know, lightning, ice accumulation on tall structures, like all that sort of stuff that matters a lot for planning purposes, we're still not all that great at. And really, really focusing on generating realistic past time series for locations where we don't have direct observations, where we don't have 60 years of data of like, ice accumulation, which is pretty much every single wind farm anywhere in the country. It would be great to prioritize that. And then you could start working on like, variability generators. We'll use those models to generate alternative histories that are, that aren't the exact trajectory of the past. And then you can do, that really helps you do attribution studies and all that sort of thing. I would put all of that like as a priority relative to like 30-year, 40-year runs in the future. Because if we could do the past time series well, we could, through statistics, fancy versions of extrapolation, we could, understand the climate, the expected climate of 10 or 15 years from
now. Okay, so I want to come at this from, first of all, I want to throw my hat in the ring of the scientific vision is the key thing here. And yes, you can link it to people, because there is an imperative that we get some of these things right to help people broadly, right? If we want to get into stakeholder discussions and things like that and making data availability, I'm just going to tell you, in my view, it's a red herring, and you won't get it done in 5 years, right? And here's why. So my prior comes from my past research view and now my current business. And trying to define what a stakeholder is an infinite problem, and what they want is even more infinite if that's possible, right? So going back from my previous research career, we used to have a joke 25 years ago, what makes a good ensemble? Well, the answer is it depends on the norm, right? Because you're going to care about somebody different from you, something that you want that's going to help you make a decision that's different. I don't even think we have a definition here of what a stakeholder is. And I don't even think we necessarily want to try to say, this is our stakeholders, because there's too many kinds of stakeholders. And so that's where I'm going to come in. I'm looking forward to a spirited discussion in our practitioners and stakeholders thing. But I can just, as an example, right, we work with NGOs all the time, right? People like Gene here, to deal with underserved communities or economic groups or whatever, you need somebody engaged, right? People in this room cannot span that space. Just can't do it. So it's a broad ecosystem. This group will empower that ecosystem to go do what they do best. We work with NGOs. They can't deal with a tiny fraction of the information we can give them in their discussions with their people on the ground, right? So dumping data on the world is not the answer. So I just want to caution against that as a red herring, I guess, in the closing.
Hi, I wanted to respond to Dave's comment about confronting models with observations. There actually is a large literature in detection and attribution studies confronting models with trends. While it's not a particularly popular research topic in the United States anymore, we did feature a graphic in, I think, Don, maybe you can correct me, I think the 4th national assessment that showed 10 different observed trends that had been attributed to climate change through the CMIP models. That being said, almost all those studies are global in extent, and regional detection and attribution has proven to be a very difficult subject. Why is that? Well, partly it's signal to noise. As you go to smaller spatial scales, there's more internal variability. Part of it also is the models stink, to be rather blunt. So I guess what I hope is that that a kilometer scale model will improve our regional simulations to the point where we may be able to attribute some of these observed trends, some of which are getting rather large. And I guess that's another point. It was raised that we're almost at 1.5 degrees. By the time this project is really off and running, we're going to be closer to 2 probably than 1.5. And so the signal keeps on getting larger. Ben Santer once said to me that detection attribution is the ultimate model validation. And my response to him, this is a long time ago, my response to him, I said, by the time we retire, this will be an exercise for the undergraduates. It's not quite there yet, but I'm afraid the sobering news is it is easier than it used to be.
I'm actually quite impressed by the repeated mention about community building, stakeholder, and scientific research. One of the things I kind of like to mention, I mean, based on my observation, I myself, I was a part of the scientific meteorological scientist and numerical modeler actually for 15 years before I actually became actually researcher on the trading floor and focus on weather. And then right now I call myself more business person and responsible for making money and not so much research. My observation is very interesting and really humbled me at the very beginning. So if we kind of, when I just step into the business side, I felt, okay, I have all the scientific knowledge and those guys know the business, I go there and help them. Yeah, and their thinking is not so profound. That was really wrong. That was wrong. The stakeholder, don't think stakeholders are not sophisticated. Don't think stakeholders are not scientific. And then, for example, our company have 100 full-time employee researchers, and most of them have PhDs in meteorology and in geology, that type of thing. Yeah, some of them actually came out from very established scientific career. Yeah, and then this is 100 not even include the analysts in the business lines. Yeah, and then you really think about that. This is just a company. And then a lot of companies are like that. So they have already done a lot of work that could actually help you understand precisely in the language you need what my media need. You don't have to actually spend the time and then to go through the learning curve. They can help you get there pretty quickly. And then give you an example. One of my friends, who is actually the head of Meteorological Research Institute on Natural Disasters. And then I asked him, where is your primary database? He said, your company. Yeah, it's kind of interesting. It's kind of teaching me that sometimes even the scientific coaching doesn't have to be only one way. Yeah, so if we have that kind of attitude and think about we work together, and then that's how we're going to really accomplish what we want to accomplish. Yeah, and if we are thinking, we have the scientific capability, and then you guys have the need, and then we are going to help you, and then the relationship is we tell you what we can do, and you give me the money and funding, we're done with it. So that may not be good enough.
Yeah. Well, and thanks, Yang. And, I think to Josh's point, we can look at the bookends, right? we don't even talk to the stakeholders. Nobody's suggesting that. Or we say there's too many of them. We can't possibly deal with all of their needs because they're all over the map. That's a true statement too. So what is the right approach? It's like if there are a lot of people who don't like you, you can't go to each person and try to understand, now, why is it you don't like me? Why? Blah, blah, blah. It's like, look, I'm going to just try to be the person I am and be a better person. And I don't care about, I can't fix all of that stuff. So I don't think we're trying to, and Josh, I agree with you. It's hard to define a stakeholder, but I think what we're saying is we need to be sensitive to the needs out there, the timescales more generally, not to a specific, individual company or whatever. But if we don't think about that at all, then I think this becomes just a science experiment. And then I think we're back to where I've worked with a lot of companies and if you sort of do all your work and you provide something you think is a great solution, or you look at GMOs and things like that, it's like society said no. Doesn't matter how scientifically good it is, they said no. And so you have to really think about stakeholders and policy and all that stuff from day one, I think. But Josh is right. How do you define a stakeholder? What does that even mean in the we know what it is, but in the context of what we're talking about, how do we think about it? How do we think about engaging them? And I think we've got to figure out what is between the bookends. So yeah, John, go ahead.
So really along the lines of what you're talking about, but I think the discussion's missing the mark here. Even since I know you, Kelvin, I'll say that your vision statement sucks. It sucks. Okay, because an average person looking at that isn't going to be able to figure out what you're saying, right? It needs to be something that is targeted more at stakeholders and the outcomes that they need, right? So if it were more along the lines of, a world in which decision makers and planners have the information necessary to provide them, to allow them to make informed policies, plans, responses, whatever else. I mean, this gets at what are you enabling? And that statement isn't even specific to climate prediction data, right? Because I think most of our folks in government who have to make decisions, that's only a piece of the pie for them. And it'd be great if they had that whole pie. But within this group, we can then have a mission that addresses the climate piece of that, right? But the vision has to be much broader. It has to be very accessible, and it can't be nearly this long.
Well, right, yeah. I mean, like I said, I just wrote this morning. But you're right. I think the key thing, though, is it's about society and making decisions, right? I mean, that's the key thing about decisions in a changing climate. To me, that ought to resonate with people. It's not about how do we, improve our models? How do we get to kilometer scale? That's not accessible to anybody. But I think a general person, I'd be interested to hear what Gene and Edith think about this. We need, you're right. I mean, it is long. Just wrote this morning, but we've got to have a vision as a community, as a global community, what it is we're really trying to achieve. And if that vision is done the right way, the science becomes an automatic pathway to achieving the vision.
I 100% agree with
Absolutely.
that. It's the pathway, but that's not the story we have to tell, right?
Oh, agreed.
And I think it came up yesterday that even providing, great models with good data, that doesn't get them there. Those that have to make decisions then have to put those through some other processes that add additional uncertainties and all these sorts of things. So what they need is, in the end, what is the information that comes out at the end? Is it reliable? Is it timely? Does it allow them to make the decisions about policy and plans and response and those things that they need to make? Because that's where they're sitting every day. And we need to speak to those folks. And I think most citizens understand that there are folks in those roles that need to make those decisions. And I would think they would want them to make them as informed decisions, right? So I think it would resonate more broadly at having a statement at that level. And then, a mission statement that's more specific about what would this group be doing to contribute towards that with respect to climate prediction and other things.
Yeah, no, good points, good point. Well, take a crack at revising it. I mean, seriously, because that's what this is about. Not just talking, but let's come away with some tangible things. Say, here's what we've decided. At least this group, and this isn't the whole community, right? But here's what we came to a conclusion. Here's our vision. And we have to think about the audience for the vision, right? And that's a really, really key point of who's going to be reading this. Is it Congress? Is it, are we trying to sell this to philanthropy, to fund an effort? I mean, and part of it is you structure the vision in a way that meets all those needs. Well, then it becomes so watered down, it's meaningless, right? So you have to really think carefully about that. Yeah, Dan.
I'm just going to try one more quick political framing, and you can throw rocks at me too. I would view this more analogy with an unexpected war. There's a phrase, you go to war with the army you have, not the army you wish you had, right? And that's kind of the situation I think we're talking about. We're facing an existential crisis. You take what you have and you innovate on the fly, but you have a very clear objective and you prune the superfluous stuff because you don't have the luxury of doing 1,000 things. And that, I think that's kind of what we're talking about. We have to make that degree of compelling case to society that we're going to do something that's very clear. It will help you on a very obvious short-term time frame in ways that are actionable, right? Because that then people can do something about.
I guess I didn't introduce myself last time. Larry Kaplan from Hewlett Packard Enterprise. But yeah, I think we're moving into the right direction. So some comments were made by several folks. It's not so much the stakeholders, it's really who are we trying to convince? And it's not a single set of people, right? There is the public, convincing the public that this is real and it's going to have a real effect, which goes back to, I think, what Eileen was saying. What are the things that the regular citizen is going to feel the effect of? Well, in certain parts of the country, it may be the forest fires. We talked about the water supply issue yesterday, right? That hopefully will strike home to people who are going to have their water supplies at risk. Power generation would be another one. How do we make sure we have reliable power? So these are things that you would target at sort of the more, citizen. But then you also have the people who are, we can call them stakeholders, whatever, the people who have more direct effect. They have to be able to use the data that's generated and be able to apply it to their area of specialty. That's a different group of people. You have to go deeper with that group of people. But if you go deeper with the normal citizen, you will lose them. And then you have the philanthropy, the funding agencies. So again, to me, it's not a single target, and you can't lump it all together. You have to have the targeted efforts in each of these groups.
I'll take the challenge of just responding for stakeholders. And I'm hearing a thread, I think that I can fully support, and I think everybody's on the right track here. I, for one, support the vision, and I just want to respond in terms of, is this, research science, do you have to tailor to stakeholders? And I think fundamentally, you have a really phenomenal problem to solve, and I'm glad you're on it. But this is an ecosystem, and all of us here have a responsibility and an urgency to act on climate. But I think if you do what you do well and do it in a way that works, you can pass information on to not every stakeholder, because we can't even reach every stakeholder. And I'm a stakeholder, right? Is that message has to be tailored, but I think the fastest way to action, the fastest way to solving a problem is to make sure that you've got targeted stakeholders, or you're passing off information to those that have the ability to use it. You do want to make it user-friendly. You want to make it delivered in a message and in a way that works, but it doesn't have to suit every stakeholder. So that's just kind of endorsing what I'm hearing here. But trusted partners, I guess, who can move forward, take the information, and appreciate, again, being sensitive to the needs of stakeholders and having us in the room.
It's a great discussion. Yeah. Sorry. Go, Maria.
Yeah, I'm hearing everything and I'm still trying to process, and I'm still processing yesterday. But I think from a vision or like driving mission that drives us, yesterday I was sitting there listening to all the talks, but the one about from the US Army Corps that was sharing the dam images, right? And we all have heard about what has happened with Helene and things in North Carolina. And we are all humans doing science, and we can't really decouple ourselves from that. And we ourselves are impacted by some of these things. So yeah, I guess what I'm trying to articulate is that making it real with these extremes and these stories can sometimes help with a vision or mission, even if it's not an exact stakeholder that we have identified. So yeah. But I'll continue listening and learning. Thanks.
Oh, sorry. You have a question there? Let me see if I can get it. This is under chat, right? I'm going to read this one. Great idea and absolutely love the vision. There you go, John.
Look, can you hear me? I'll comment directly if you can hear my audio.
Please go ahead.
Yeah, so John England from the Army Corps Risk Management Center here in Lakewood. I would submit, you know, this is a big task over the next couple days, right? So focus on this vision. It took us 9 months. So when we just finished the Academy report on PNP, people don't know what PNP is. So, you know, I could echo the comments about minimally biased, fine scale. But my suggestion here for forward progress is really get the audience dialed in for this vision so the project goes forward and gets funded. And so the missing piece, I would say, is economics. So you could do floods and droughts. I'm a hydrologist, so that's what impacts, you know, the ag sector. So get the vision and have some key pictures for the storylines that will sell to the average public and to the next steps on funding sources through Congress. I think that's what you need to focus on, which is really difficult to do, but some key pictures could be dam failures, could be crops crushed by hail, could be the wildfires in California. We're all familiar with those cases and they're in the IPCC reports, but having that message clearly at a global level is difficult. So you may want to also focus on what's impacting Europe, right? What's impacting the US? What's impacting South America? And that gets muddling the message. So suggestion, I guess, is to focus on some economics and impacts broadly and have key pictures on the products that will be provided. Thanks.
Good points, John. Thank you. Could you switch and put up the, when like John is speaking, could we see his picture? Could you do a switch to the?
Unfortunately not here, but people on the screen.
Oh, okay, gotcha. Okay, thank you. Great, great. Go ahead.
Yeah, maybe I'm a little bit critical here, but like it seems like we're mostly a group of scientists in this room, and we try to, like, it feels like to me we're trying to formulate a mission for stakeholders. Whereas it would be much more impactful if the stakeholders say, this is what we need, and they drive. And the answer is high resolution modeling. Like, I think like having, I'm a little bit concerned that we do the opposite here, that we say we have high resolution modeling and it's great for stakeholders. But having the call from the stakeholders, I think, would have a much higher impact. That's why I think that having a clear science mission would be also really good to have. And I brought up the science missions of CERN and of the James Webb Telescope. And CERN is to gain a better understanding of the fundamental laws of particles of the universe. And the James Webb is to answer the key questions about the universe and make groundbreaking discoveries in astronomy. Like, again, like very much shorter, but also very science focused. And I think that has value and has weight as well. And like those programs are transforming our understanding of the universe.
Okay, Andy, before you sit down, so those are the missions of science organizations, but if a stakeholder looks at that, they don't see themselves there at all, right? So
that's very true.
So you're saying and we need different visions or mission statements or whatever for different groups, right?
I think we have to decide what we want to do. Like if we really want to improve the science, we should be clear about that. And if we want to really engage or do this for stakeholders, I think it would be way more impactful to have the stakeholders raise this issue and say, we need this. And you have to deliver. And we say, okay, we can do this with high resolution modeling.
Mm-hmm. So you could sort of, you know, again, this gets really long, but that's okay. We're not wordsmithing. We say that makes these decisions, you know, driven by science or driven by transformative science or something like that, and not necessarily kilometer scale models, but or it could be, but you know, the science part's not there at all, really. It's just it should say that this enablement is made possible because of science somehow, or find the right words. Yeah. Okay. Gotcha. Yeah, that's good. Thanks.
As a small comment, I think that I'll disagree a bit with John online and maybe channel some of what Andy was saying. I think that you mentioned the Apollo missions the other day, and the Apollo missions, when we talk about stakeholders, obviously there's the economic stakeholders. You need the economics to get through Congress and stuff like that. but everybody on the planet is a stakeholder in better climate science, and you need an fearful one. So I think we need to channel something like the excitement that came from the Apollo missions. And that's something that, this is a grand challenge problem. Let's do that. I've been playing with a few ways of doing that. I haven't come up with something yet, but let's not make it just about doom and gloom if we don't do this. Make it about a better future. Yeah.
Hi, my name is Jack Chan. I'm with Metropolitan Water Reclamation District, Greater Chicago. It's a long name. So I guess I'm one of the practitioners. I'm a civil engineer by training. So I think it might be helpful that we kind of step back a little bit before we even be talking about the vision. What is the problem, or what are the problems that we're trying to solve here, right? So obviously there are scientific, problems that we're going to address, but there's also practical problems, engineering problems. What are those problems? And I enjoyed all the discussions that we have so far, but in the back of my mind, I haven't seen that overarching, picture of what are we trying to do here, and what are the problems that we're trying to solve. It doesn't matter whether it is a scientific problem or is a engineering problem or otherwise, right? We have to have that very clear definition. We know those problems, and that's related to the stakeholders. And the stakeholders in this case may not be, individuals. It could be a whole sector, like the public or industries, right? So what are the problems that these industries are dealing with? And therefore, what are the data that we're looking for that are missing right now? And what is this vision allow you to achieve to be able to provide that set of data? I think stepping back will help us a little bit more. And that might be one of the breakout topics that we have to discuss later on. Thank you.
Thank you.
Good morning, Kelvin. Thank you for the invite for being here. I was not here yesterday. I'm Mark Bove. I'm a meteorologist with Munich Reinsurance America. I'll try to disregard the laughs at the insurance industry earlier. But I can come at this from both a stakeholder and a scientist perspective. I'll give a couple examples. As a stakeholder, the reason why I came out here to Champaign is, our GCMs today are good at identifying climate trends that are large in scale, both temporal and spatial, and also last for a long time. Where we need information in the insurance industry is for very fleeting, small scale events like convective storm, wildfire, that are not currently captured in any of our current TCMs that have a resolution of 100-kilometer grid over the entire Earth. Now, 1 kilometer would be a lot greater to get there and start answering the questions. But yes, we do need input. That's what my industry, particularly property insurance, really is most interested in. But there are dozens of other stakeholders. But I want to take one of the comments from one of the women on this side of the floor, because I was also a chapter author on NCA 5, that was released earlier this year. And I would participate. And in this case, I was one of the scientists talking to the stakeholders of the NCA 5. I was in the Northeast chapter region, and we did local events for local stakeholders of the report. And go in very excited. We're very proud of our report. And then we get feedback with the local people, including Philadelphia's water system. And the people are like, this is entirely unusable for the stakeholders because it's all science. If you're not a scientist, just handing them data, even in a well-written report, is not going to do it. So in my 24 years with Munich Re, I've ended up becoming a climate and meteorology translator for that field that helps translate it. But I do have to agree, getting more stories out there is important. That's how people connect, not through the data, but stories and ideas of what other people are doing to try to solve these problems. And this is what this model can help try to inform. The other thing is, I don't think the entire public really is a stakeholder. People have been complaining for the past week, oh, there was no warning of the floods in the Great Smoky Mountains. The meteorology community was blaring that for a week plus, that our models were showing a catastrophic event. There's only going to be so many people that take this information, and we should not necessarily try to cater to meet that crowd as well. Thank you.
Thanks, Mark.
think you were first.
Okay.
I wanted to point out something and maybe just connect some dots between some of the things that have been said and the people in this room who include the people who actually build computers. And that is that in terms of, not just putting a giant netcdf file somewhere, if we do build a 1 kilometer model, actually having the computational systems to analyze this, that's something where we also need innovation. And certainly, I'm in a very luxurious position that I have access to a lot of compute. But that's something that I think is also worth discussing in terms of particularly the new methods that are coming that I'm certainly using and developing. And in terms of understanding how we can accelerate delivering actual information and not just science to stakeholders, thinking about, okay, well, if I have this 1 kilometer picture of what precipitation is going to do, how do I actually communicate that in, a fashion that actually is actionable, not just in terms of, raw data, but actual analysis.
So I wanted to go back to this idea of what it is we say we're going to do and what we can do, in the sense of with the Apollo program, there was something very measurable and observable that happened. People landed on the moon. Here we talk about giving you essentially perfect information for you to make decisions, but it feels to me like it's more an incremental improvement in how reliable the information is and how granular it is and how well it can support your decisions. But there's not a sort of visible end state of now we're done, right? We're never done. So how to craft a vision that shows a step function in our, in how reliable this information is to people who, to at least, half of our community that is anti-science, that doesn't believe we can produce predictions. I mean, they say, well, they can't even predict the rain. Well, that's not true, but that's what they think. So thinking about how do you communicate the incremental gains, which might be huge, to a population that may be skeptical of science in general.
That's a really great point. It makes me think about, as you said so well, that the Apollo program had this immediate, tangible, hey, we've succeeded. Once they came back, we succeeded. But here, I think the scientific community, just like with the black hole shadow and things like that, would say, yeah, we made it. But then how long does it take for that to get into the system to where it's realized and people recognize, hey, it's really better. And the weather models, yeah, they're down at a few kilometer resolution, very rapidly refreshed and things like that, assimilating radar data. The forecasts are much better. The forecasts today of 5 days are as good as 3-day forecasts were 20 years ago, whatever the metric is. Do people really realize that? And that's been transforming. It's been in place for a long time. So that's a really important point. There's this time scale of absorption of advancement that needs to happen, and it's not going to be at all obvious. And I'd be very interested to hear Mark and other folks from the reinsurance and other communities how long they think that if we were able to give them right now the kind of stuff we're talking about that might not be available for 5 to 7 years, how long it would take before. Not before they could implement it, but before they would start to see a recognition of the value. That's a really interesting point you raised. Yeah, Mark, I don't want to put you on the spot, but if you and others want to comment on that, but go ahead. We'll go over here and then maybe have some time to think about that.
Yeah, so actually it's very much related to what just has been said before. So I was wondering, with all the discussion, how important it is to manage expectations, because it's very good to have a nice vision of better society and so on. But the problem is that, in my experience, what climate models will bring is quite a grim view of the future. So with a negative forecast, how do you translate this into a positive message is the first question I have. So at the end, as a member of the general public, I would be more interested to know of
what can we do to make it better? And that's not at the end the role of the scientific community, at least maybe not the one here in the room, it's more for the stakeholders. So in the way of having a better model allows you better predictions, but you do predictions that are maybe 5 years ahead, and then everybody has forgotten that you have done this prediction. So I have a bit of the concern of this management of expectations. So really how far we can get, it could be better, as was just suggested just before, to see of the incremental improvements and try to position them as an achievement and that others can profit from. So I don't really have a solution, but all these kind of thoughts came to my mind of what really is, if we put this on the scientific perspective, I think it's something we can really rely on. If we open it broadly, like for everything, and we are responsible for everything, it's gonna be dangerous to manage, to promise something that you can really hold on afterwards.
Yeah, no, good point. It also reminds me of the important question that always needs to be asked is, are we doing the best we can with what we now are producing? And I think the answer is really no. Chris and I were talking yesterday about some of the data that is there that is inaccessible. So some changes that could be made that would create substantial improvements now with what we're already doing. And that's something you hear a lot on the Hill. Members of Congress say, okay, this is what you want. What are you doing with what we're already giving you, with what you already have, with what you're already doing? Are you doing as much as you can with it, extracting as much value out of it as you possibly can? And that's a very appropriate question, I think. So, this is really great discussion. And we have in a different part of my agenda here, we have, I think, about another hour-ish or so to continue this. Where are we at here? Sorry, my other 9 to 10:30, yeah. And then we have the break and the breakouts. So I think what we would like to do now would be to, we have a half an hour break too, so we don't want to break quite yet, but I think if we could now come to some agreement on the breakout topics. I think what you all have been discussing here is fabulous. I think it's just, man, you're bringing up some really important points, and it just reinforces how daunting this really is. But we can pull up, and if you have your computers, you can pull up on the Summit website, Deanne. I believe we have the questions, the breakout topics that the planning committee prepared in advance, right? I think they're there. They're under resources and read heads and so on. And I'll get that up on the screen here. And I've also taken some notes, and I think others certainly have on the planning committee and the nucleus team, and all of you have. But I've just sort of realized that a lot of these are things that we'd already put in the challenge sets. Let me see if I can find what I wrote here. Yeah. So they kind of fall into the same buckets, right? The compelling science agenda. What are we trying to solve? What are the key problems scientifically? We talked about that in the pre-summit intensives. That's very important. We can deep dive on that. The stakeholders and community engagement and so on. Practical problems, what the drivers are there. Building the global community, the mission and vision, what we want to achieve, and different audiences. And then the data and tools, I think, is a really important one as well. But let me put those up and be thinking about it. Maybe we can come up with, again, we've got 2 breakout sessions, 5 groups in each of the 2. And the idea was to have each breakout session maybe take 2 or 3 topics and cross-pollinate to some extent. If you do total cross-pollination, people tend to say the same thing. But anyway, and we can write these down as we go, but I'll go ahead and put these up. And if there's anyone that has additional thoughts and questions, please come forward with them and let's continue the dialogue. But be thinking about how can we frame these as specific topics that we can come away in the breakouts, not with a zillion more questions, but with some answers of here's what we need to do going forward. Here's the science agenda. Let's draft a science agenda. Let's do it. It won't be perfect. It'll be a straw dog, but let's put it together and say, okay, we came away with something that then we can look to share more broadly and keep this train rolling down the track. So I'll go put that up here. And Maria, did you want to go through anything from yesterday? I wasn't sure now if that was necessary, or what are your thoughts?
I was coming to the mic because I have a question. So we've spoken a lot about extremes and human impact and what do stakeholders want. But the reason we're all here is because we need a special computer for this kilometer scale modeling, right? And I heard a lot about HPC requirements yesterday that were great, and we heard some this morning. But I'm wondering if we can do some translation from someone who uses these machines, myself, let's say I'm using WRF and I'm running on kilometer scale simulation. I know generally how it works in terms of if I select this many number of cores and this happens, my tiles go and do the calculations and they come back together every time step. But like, can we get more specific about the exact thing that we would solve with this climate computer? And I know this is getting into the weeds, but I'm just thinking we're here because of this climate computer that's needed. So yeah, do we have a map or something of it? Kelvin?
Yeah, well, I was just kind of seeing if other folks would maybe want to respond to that. But you're right. I mean, that's kind of why we're here, is that, like I said, the one side of the coin is all these models being developed. The other side of the coin is the computational system, which we don't have. And that was really the fundamental reason for getting together. But the two have to be done, we feel, in a kind of a co-design strategy. So yeah, go ahead.
I was going through something similar in my mind, and it's nice to, I mean, a vision's really good, but normally before you come up with a vision, you write a mission statement. And the mission statement answers why we're here in like one line. What are we all here for? What are we trying to do? Because I think that might shape the discussions in the breakouts as well, perhaps more than the marketing of the vision. You know, why are we here? And for me, it's you know, this should be in one line, and this probably could be controversial, but we're trying to tackle long-standing biases that have existed that meant the advice we're providing now is very poor. You know, there's a lot of work goes on in regional climate modeling where, you know, you do your best, and I agree that we need to do our best that we can do now. We're just trying to make a step change so that our best is so much better. And so, yeah, we're trying to remove, reduce, get rid of all these some of the long-standing biases that have really limited the value of the information that we can give now. But that's my view. But if people think they're here for a very different reason, then we're going to have very different breakouts. So can we sort of define our mission, which is the thing that underpins ultimately that vision? And I think it touches on what you were saying, really.
Right.
You know.
Right. Yeah, and I think it's always good to go back to the foundation of why we're here. And so let's see if that's here. It was this. I mean, this was what we wrote in the NSF proposal, that we postulated that the creation of this specialized computational system, we said, for these models, coupled or tethered to AI, to improve understanding and produce more accurate results, educate the next generation and meet stakeholder needs. That was the singular reason why we came together, right? And so it compelled us to look at kind of the pre-summit intensive, the state of models, where we're at today scientifically, what the gaps are in parameterizations, the importance of resolution, and so on. The AI, what it's doing now, what it potentially could do in the future, the computational framework, where we were at with Green Flash, where we're at today, and so on, and then the stakeholder community. And so we really focused on this, but in a broader sense of the goal we said for the NSF proposal was to get the community together and figure out if the community could come together to do something like this. That was the hoped for outcome. Is this practicable? Is this something we as a global community could achieve? And if so, what would the contours of that look like? That's really why we're here in a nutshell. Yeah. Yeah, Stefan.
I guess maybe a brief comment on why what we're here, like eliminating. It's great to say that we want to eliminate longstanding biases. I would love to translate that into like a falsifiable threshold, or like what is the sort of what is like the result, what is like the level of result that we think that is needed by stakeholders? What is the level, what is the quality of results that we think is actually potentially achievable with this? I think that'll make it much easier to make a concrete case for this.
Yeah, that's good, and that's something that I think would be really appropriate for a breakout topic. Yeah, John?
Yeah, so I think Francina said something really important yesterday, which is that, you know, IPCC is about mitigating and preventing climate change, and this effort is more about adapting to it, and that's why the 5 to 10 year timescale is what's targeted, and that's what makes it different from the current way that we're approaching this. But oops. Yes,
John, could
Mark?
you clarify when you say 5-10 year, you mean to realize this, not a 5 to 10 year simulations, right?
No, I'm saying what I've heard repeatedly from the stakeholders is that they're looking at things that are actionable in the 5 to 10 year time horizon. So they'd like answers in that horizon,
sure.
not for 100 years or 40.
No,
years.
but out to 30
No,
years,
not
30
even
years.
30,
30.
out to 30. Up
30 is the outer, sort of the outer
is the
range.
outer limit, but I kept on seeing on slides 5 to 10, you know, but
Oh, for
30 is
sure.
in
Yeah,
there.
it's a continuum,
Sure,
right? It's
but-
literally from
so-
weeks to out to multiple decades.
But, you know, adapting versus mitigating are two
Right,
different
Yeah.
purposes. And so we had been workshopping this in the background here. So develop a high resolution climate computational framework to serve as a time machine, can reduce uncertainties in near-term climate projections, to support critical decision-making for climate resilience at both local and global scales.
Mhm. Yeah, I mean, that captures it well, I think, and it puts the science there. Yeah, yeah. Well, let me just kind of walk you through what we came up with as a planning committee, and also as a nucleus team contributed really wonderfully to this. They're kind of long, but just kind of look at the bold text for right now. And you have these online. Enhancing but not replacing existing capabilities. There was great sensitivity, I think, as we were putting this whole thing together to not disenfranchise an important part of the community, and making sure that these efforts were not seen as being marginal or not helpful or whatever. They do provide value, but as Mark said a little while ago, you know, there's a limit to the capabilities there. But you can't argue with some of the great stuff that's happening with downscaling and other things. But there are real limitations. And again, the community has owned up to that. So I think the question is, how do we make sure that we advance science and so on, and don't leave anybody behind? That's really key. And that was something we gave a lot of thought to. I think Barb talked about the interoperability of Earth system models. There are a bunch of them out there. And so how do we do something that doesn't basically say there's only, you know, 2 can play in this sandbox or whatever? But if we have everybody playing in the sandbox, then we're right where we're at today. And you know, it's not going to be, it's not going to make sense. So that's a really important question. Dan, I think, talked about this one, political action investment. He's continuing to talk about this. You know, what is the storyline that motivates action? And by political action, we're not really talking about going to the Hill and asking for money. I mean, political action means a lot of different things. So there's ultimately, you know, this plays to everyone, the importance. And his point here about facts-based arguments, they're necessary but not sufficient. Telling stories, showing pictures. Although I kind of feel like sometimes we've done that a lot, and you know, it just doesn't matter unless it's happening in your district. But that's really important. Cost and capability, obviously, it gets back to what John Schauf was talking about yesterday in the HPC world. Equitable access to climate information, something Francina has been very keen on and very important. And the access, as we realize, that doesn't mean that you just throw the data over and hope people understand it. There's a much richer storyline behind access that involves you know, tools and understanding and things like that. Leveraging the expertise barrier and running these models. This gets to the capability. We talked about this of how we make sure that from day one that grad students and others can run these models, and the learning curve is not so steep. It's very, very important. The barrier to entry is lowered as much as possible. And we're seeing that now with AI. I think it was talked about in the context of AI. That's very important. Effective use of data and output in decision-making kind of gets back to what we were talking about before. And I think somebody just mentioned, you know, how do we evaluate to see if it's adequate? You know, what are we targeting? What is the issue here that we're trying to deal with? Frameworks for producing useful results. Again, high resolution modeling, statistical and experimental frameworks that need to be put in place, again, to improve the understanding and not just throw a bunch of data out there. Data in, output out. Again, it gets to the volumes here. And you know, we mentioned that we hadn't been talking about data. Well, a lot of it is here. You know, huge amounts of data needed to put the models to be put into the models, but they also output much larger quantities of data. So how do you address that? There's a lot of end user needs out there. Everybody doesn't have high performance computing. What tools, what strategies? Again, and talked about output during runtime and even training AI models during runtime. That came up yesterday. Measuring model capability metrics, it gets back to the point of, okay, what are we trying to do here? You know, what are the values? What are the accuracies? What are these things? That's a very important scientific question, but it's also something the users need to be in on. And what do we treat as truth? Workforce development, another important thing that is critical as we think about moving forward on these different fronts. There's a lot of things in terms of data science and so on. I mean, my own doctoral students, you know, trying to take courses, we're so oversubscribed at this university in terms of computer science department and stuff. A lot of it's only open to majors. So how do the other students learn? And that's, I'm not ragging on the University of Illinois. We've got extraordinary things, but we're teaching our own classes. Christy, if he's still here, he teaches some stuff in machine learning, and other people do. But we're not computer science experts, you know, and data scientists. So we really, I think, have to think about how we you know, bring these communities together in the educational realm. So that was what we had come up with, and you all have brought up, I think, some other really extraordinary other topics here. But I think the point here is let's come to some agreement on, at least we don't have to write paragraphs, but okay, what are the 6 or 8 or 10 or whatever topics we really want to do in the breakouts? Because we're going to spend the next several hours in breakout groups coming out with, okay, Chris mentioned the science agenda. Okay, then come up with a science agenda. We're going to challenge you to do the work, not just to say we need it. Dadgummit, let's do the work. And that's what we're here for, right? Roll up our sleeves. That's why it's a summit and a workshop and not a conference. So, so we've got the right people in the room. I can't think of anybody better suited to put meat on the bone here. So that's our task. So we've got about another 45 minutes. And if I could maybe invite some of my colleagues from the planning committee and the nucleus team to come up, and let's help folks put this together. Okay, so don't be shy if you would. Yeah, Francina is going to lead the way here. Were you? I thought you were. Maybe you're just adjusting your chair. But again, these pithy statements that are going to be, okay, what are the breakout topics? Again, as I mentioned yesterday, this is your summit. We want to make this happen. We've got to figure out what we need to really talk about in detail. So, okay, and I'll kind of be the scribe here.
So Kevin, are you asking us to now try and start self-selecting for the breakouts, or what would you, where would you like to go?
No, great point. So there is a spreadsheet. Thank you for that. There's a spreadsheet, a very colorful spreadsheet out there that shows the 5 different breakout names. And let me grab mine.
Yeah, I'm sorry. I didn't say that properly. I don't mean self-select into the breakout groups. I meant for the breakout groups to select their topics.
Yeah. So what I'd like to do is not do it by group, but just in a plenary right now, kind of collectively come up with the topics, and then we'll parse them out across the breakout groups. So, but to your point though, there are, again, 5 breakout groups, 2 breakout sessions. There's 2 of these breakout groups we call cross-cutting, okay? And then there's one AI and Earth system models. There's one on practitioner, stakeholders, and end users, and there's one on the computational system. So that's how we set it up. Now we can tweak that, right?
Right. So I mean, for computational systems, right, I could see us looking at some of the interoperability or model framework stuff, the costs, both CapEx, OpEx. Those are things that, would be, to me, would be really good for that, for the computational breakout.
Yeah, exactly. And so we don't, that's a really great point. We don't have to, invent new ones, but there are some of those, as he just said, that speak exactly to these issues. But there are, I think, gaps based upon what we talked about today that we might want to come up with some additional ones and not use the ones here. And I apologize that, again, we didn't make hard copies of these because we felt it was better to just put them on the web, and hopefully you all are looking at those now. But I do think, we need to come to some agreement on these. So. Yeah. Oh, okay. Yeah, Francina pointed out that if we made them, just took out the text, I think it just put the headlines there would be good. And just so you know, all of you have been assigned a breakout group, pre-assigned. Those of you who are here have the flexibility of moving around a little bit. Those who are online don't, because we have to hit the magic button on Zoom and it vectors them into whatever breakout group they've been assigned to. But when I did the orientation for the nucleus team, there is, in each breakout group, there is a chair, which is a nucleus team member. there's a scribe, there's somebody monitoring the incoming questions from online, and then there's somebody who's been designated to report out. Now, all of these folks are obviously in person. And if you get in the room and say, hey, I don't want to do this, nobody said that. So if you don't, that's okay. Just, we got to have somebody doing each one of those functions. Okay. So the chair, the scribe, the report out, and the person monitoring the question and answer. When you go in there, there will be a computer already set up that's already, ready to go. It'll have the folks online there and so on. So it also shows the people that are in person and the people that are virtual. Okay. And the rooms assigned are the ones, they're just out here, and then there's some around the corner. The big room is for the computational, for the Earth system model and AI. I think that's isn't that the big one? Yeah, that's the big one in this so-called quad room. Yeah. So, yeah, go ahead, Chris.
I'm sorry to take us back to basics here, Kelvin, but to me, the elephant in the room is actually making the argument that we need a new dedicated climate computer. And you may consider that to be a settled problem. I mean, after all, I think it was why you even set up this meeting, is because you had concluded that. But I think from the community point of view, that argument that's not a settled problem. Is that the best strategy for moving kilometer scale modeling forward, assuming that's an investment the community wants to make? And I think it's not a fair starting point to say, okay, and this will be somehow funded by philanthropy, because I think that's, it's a convenient way of saying we shouldn't worry about the cost, but I think it's not a realistic assumption. I think it's realistic to assume that it's something that will require an investment that will probably come out of other things. And so it really is something that has to be played against other options.
Yeah.
And in particular, the reason I bring this up right now is that a breakout topic, or are we going to take that for granted and not have the
that's a great point. It is axiomatic that we are not going to relitigate the question of, do we need a special computer? We came into this, and NSF funded it with the notion that we were going to talk about that. So we're not going to say, do we need a special computer or don't we? We're coming under the assumption that we need some type of specialized computational system above beyond what we have now to do the things we want to do. That's axiomatic. That's baked in. We're not debating that. That's a given. How we do that and how it's funded, those things need to be looked at. And I disagree, Chris. I don't think it's beyond. We're talking $2 to $3 billion. As somebody mentioned yesterday, I think, Dan, you mentioned the price of ITER and LHC and stuff. This is a small investment for a hugely important problem that many large, very, very wealthy companies are heavily worried about. So I don't worry about the money. I worry about working together and getting the community together. That is the big problem I think we face. Of all these different groups developing their models, putting major money in them and saying, I don't want to give that up, and they shouldn't give it up. But the goal of the question is, how are we going to do this? And should it even be done? But no, we're not going to debate whether or not we need the computer. The NSF funded this project to talk about that question. Okay, very clearly. I want to make that very clear to you. We're not going to debate that issue.
Well, so the question though is, and I think is the subject of debate, is what does that mean?
Well,
because I just want to finish that thought, right? Specialization can mean all sorts of things, and they're in cost and capability, which I think is very central to that discussion. What does that mean?
Right.
Because there is a large spectrum for how much specialization you can do and afford.
Right. And that's a question that is up to us to answer, not me. Okay, John Schau presented all this stuff yesterday, and we're not there yet. But again, this is not about asking questions. This is about finding answers. So it's a great question, but it's up to us to figure out, what does that mean? Okay, well, right. What does it mean? I think we all have our own views of what it means. And that's why we came together, is to say, okay, let's see if there is a consensus on what that means. If you go back and look at the proposal, look at my talk, look at all the stuff we sent you in advance, it teed all of that stuff up. So that's what we're here to talk about. John, you want to address that point directly first before we?
I will. So we've been assiduously avoiding engineering a machine on the spot. We have some smart computer architects in the room, and that's why we invited them, but we're gathering requirements to find out what's hard and what isn't, and that's not the same as engineering. It's requirements, and we do see that the next step after you gather requirements is to then put some alternatives on the table and analyze, how far can you push those alternatives? That's the next step, but requirements is that my presentation didn't pose an architecture. It is a set of requirements, and there are some that are daunting that are off roadmap. But that doesn't mean you have to do a completely specialized machine. That's not, we're going to put a specialized machine on the table, but we also have a number of compelling off-the-shelf solutions that could also be put in. And we're going to see how they play out.
Yeah, and that's why we call it a specialized environment, not a machine, because we're really not talking about a machine necessarily. It's an environment. We want to keep that really, really general. And so we're very careful to be specific about that. And so there's a lot of flexibility. And I think that deep dive in the breakout needs to really talk about what is it we still don't know, right? I mean, Green Flash was 13 years ago. We had a lot of lessons learned. DOE had this massive report on exascale, right? There's tons of stuff out there. Surely we've learned a lot since then about how to do some things. And so what is it we're trying to achieve? As you say, it's requirements driven from the modeling side. And what do you have? What don't you have? What do we need? What are the science questions? And this is why we did the pre-summit intensive, to go back and forth on that. So you're all raising exactly the right points, but I'm just saying that it's, John said it very well, and this is where a lot of people get confused. We're not saying we're going to build a bespoke computer only for a climate model. That's not the goal. We're talking about a specialized, and that term specialized doesn't mean single purpose. It means a system that is co-designed with a code in mind to achieve the kinds of things we want to do in a reasonable time frame. And in the proposal, we said 100 century level simulations in a year. That was a kind of a stake we put in the ground and said, who knows what, but if you did 30 ensembles, say 50 ensembles in 6 months or 5 months or 4 months, pick your favorite thing. But right now it takes us 10 years to do ensembles with the atmosphere only. We know that's not enough, right? So what is the sweet spot? That's a question to be answered that we're here to talk about. Yeah. So Michael, yeah.
So I'm completely with you on trying to assess what we've learned since Green Flash in 2011 or whenever it was. Back then, and Tim Palmer alluded to this, there was a similar international summit, larger one actually, at the European Center. I'm sure that some of you people were there. Jim was there, I think. Dave was there. I was there. I think it's fair to say, and we discussed this a little earlier, Kelvin, that summit failed because we don't have a kilometer scale computer. This is the same thing we were talking about then. So my question is, have we learned why that failed? And how can we avoid that? I don't know. I don't know the answer to that.
That's a good question. Yeah, that's a great question. Yeah. John, do you have any perspectives on that from your point of view?
I did not attend that summit.
But I think Michael was just talking about something even more broadly that not so much even the summit, but the Green Flash, why wasn't it realized?
Because we thought the Moore's Law was alive and kicking then, and we'd be eclipsed in 3 years, but it didn't. Yeah. Well, yeah, okay. All right. Michael next.
Yeah. No, good discussion.
The real reason is people thought we were nuts. They said, oh, you can never do this on a cell phone processor technology. So we demonstrated that. We demonstrated we could do it on parallel cell phone processors. And we ran Dave's code actually, at supercomputing a couple of times. I think the reason was that people just didn't want to, well, I don't know why they didn't. I mean, I presume it's because they didn't want to fork over the money.
Yeah.
But there was also a lot of contention about, well, we don't need this, and I don't know. I mean, Shukla had this great, meeting with a lot of, serious, high profile people in it, and it didn't work.
Yeah. Well, and you're right. I think certainly what has changed since then, right? Well, computing has changed, politics have changed, science has advanced, technology has advanced. And I think 13 years forward, fast forward, we're in a very different spot today than we were, even with even though a lot of people are still climate skeptics, I think that has changed quite a bit too. So I think we're at a different time, which excites me, Michael, to your point. I think you're absolutely right. But the changes that have happened in the intervening 13 years, I think give us the possibility of doing something like this. But I don't think business as usual is going to get us there. Now, AI, as something we were talking about the other day, that with GPUs, they have the raw capability, but will they be able to deliver the kinds of performance that we're talking about? Maybe 2040, but to Francina's point, well, that's quite a long time from now. Yeah, Jim.
So I've got a question about scope. This is an international symposium, and the Europeans have done really an incredible job with Destination Earth in articulating the reasons. How much is this really an international effort, and to what extent can we build upon what they've already started?
Yeah. That's a great question. I don't know, Tim Palmer, are you on Zoom? Or Bjorn?
Yeah, I'm on.
Oh, Tim. Yeah, great. Please, would you like to, did you hear the question?
Well, is this, the question was, is this an international activity? Was that the question?
Right, and it involved, the question about destiny and, how are we engaging them, and is it truly an international effort, right?
Well, I hope so is the answer. But I wanted to, I've had my hand up for a bit because I wanted to respond to a couple of things. In some sense, the summit didn't completely fail because there is actually a line that you could, or a linkage you could draw between the summit and Destination Earth. It took a few years, but the momentum of that summit actually in some ways led to the Destination Earth project funded by the European Union. So I like to feel that summit wasn't a complete failure. But I would say the main stumbling block that we came against, and probably still today, is from the institutes that develop the CMIT models, who feel somehow threatened by this activity, either threatened scientifically or potentially threatened financially. I'm sure some institutes thought, well, if government's going to fund this, where's the money coming from? It might be coming from my budget, and that led to a certain amount of negativity, I think. The other thing I just wanted to say, since if I've got 2 seconds, is that although this goes back now about 15 minutes, we were talking about the motivations for this project being mainly in the adaptation side rather than mitigation. And whilst I agree that adaptation's a super important reason, I don't actually think that it's quite as one-dimensional as that. And I'll just give you some examples. There's a lot of talk these days about tipping points, whether we're entering or about to reach a tipping point, either in ocean circulation or in the cryosphere or the tropical rainforest or whatever. And of course, the whole point about tipping point is that mitigation after you've passed these tipping points is ineffective. Now, again, come back to low resolution models. They just don't do tipping points adequately. The AMOC is just a slowdown. There's no evidence for tipping point in AMOC simulations in CMIT models. Now, this is a kind of mitigation question because it determines how fast we should be trying to mitigate climate change. If we want to avoid tipping points, then if we have some credible, or at least more credible way than we have now of predicting them, it will have implications for mitigation because it will tell us how quickly we want to, or we could mitigate. The other point about mitigation is that, of course, a lot of work these days in mitigation is developing renewable energy technologies, and that's certainly true in my own country, where vast wind farms are being put out in the North Sea, and so on. But it kind of raises the question: Are we sure that the changing climate, the circulation patterns of the changing climate are going to produce the amounts of wind and solar, for that matter, that we want in future? So if climate change is going to make currently windy places less windy, for example, by increasing long-lived blocking, or making currently clear sky regions more cloudy, then they're not going to be as effective. So again, I think that's a very practical reason why having high resolution simulations are important. I mentioned in my own talk the whole area of geoengineering, which I think is coming up the political agenda again. And we just can't answer those questions about what aerosols are going to do to the monsoons, stratospheric aerosols do to the monsoons, without having credible high resolution models. And the final thing I just want to mention is attribution of specific systems like your recent hurricane. How much can we attribute the rainfall, for example, to human climate change? I think that's important for two reasons. One is the discussions which will probably dominate the coming COP meeting in Azerbaijan on loss and damage in the tropics. If we want a sort of a scientific way of attributing specific events in developing countries or global south countries to climate change, we do need a more rigorous methodology than we currently have. And, I think in the future, there's going to be a lot of, whether we like it or not, there's going to be lots of litigation suits brought against, fossil fuel companies. And we'll need the evidence, the hard evidence that these events, because otherwise, any decent lawyer, I think, worth his or her salt will be able to unpick any serious attempt to mitigate events against climate change if it's solely based on CMIT models, because they'll just be able to unpick all the biases and things and say, well, how can you possibly say anything credible given those biases? So I think the whole reason, I mean, leaving aside the scientific understanding and the thing that John Petch mentioned of reducing biases, which absolutely is what motivates me, there's a whole raft of reasons why this is important societally. It's not just about adaptation, although that's, of course, a very important part of it. Thank you.
Thank you, Tim, so much. And I'd like to go back to the part about destiny. In putting the summit together, you're right, international summit, we reached out to all the different groups around the world, Japan, Europe, so on and so forth. And the idea was to bring folks together to have a conversation about how these various activities could work together better. It wasn't that this summit was the king and everybody had to come and do what we said. It was how do we work with, bring Destiny and all these other groups together to say, okay, now we've truly got a global community. Destiny's done amazing things, really extraordinary, and they have built a community, as we saw. But has it been, truly a global community? I think they would probably say, hey, we're happy to have help from the US. And that's kind of what we're doing. So it's international in the sense that we're trying to bring everyone together, but we're not the total singular organizer of this thing. It's more a community of communities. And so our role is simply to join forces, join hands with these other groups to work with them to continue to build the global community. It's not like they haven't started it, for sure. And we're not the end all here at all. It was more, how do we take that next step?
Can I just say that, Bjorn mentioned in his talk about this, what I see as a kind of an overarching structure, which is called EVE. And, there was a big conference in Berlin last summer on this. And, the idea was to have a series of nodes of some very highly coordinated network of exascale computing centers that would ensure that these kilometer scale ensembles were done in a very highly coordinated way, and that the data was made available to everyone in the world. So I would just encourage you to think about the EVE concept that Bjorn mentioned as a possible overarching global international structure to kind of position this US NSF effort within. Thank you.
Yes. Go ahead.
So I'm reminded of the gentleman yesterday who said he's too embarrassed to go sit back down because what he was going to add has already been added. So I just wanted to kind of also emphasize this point that I think a real cross-cutting topic for these breakout discussions should really be how do we facilitate this international collaboration on something like this? It's a fairly, complex issue. Going back to one of the things I was going to say, I agree with what Tim just said. I don't think the previous summits, I wouldn't use the word failure, but what lessons can we learn from that? What can we do better a second time around? But also when it comes to collaboration, I think again, Tim has a valid point in saying perhaps some groups feel that there's a competitive aspect to this that makes them uncomfortable. But it's not as simple as that. Here in the US, and I'm thinking back to the Academy study that Chris Brotherton chaired about advancing US climate modeling. One of the things that becomes apparent when you really think along these kind of lines, it's not just the people, whether or not they want to collaborate or not. People work for different agencies, right? And agencies have different missions. And I think that that is a real, thing that we need to think through as well, right? So anyway, I think this general point is really worthy of some deep thought and discussion about how we bridge some of these challenges in truly collaborating together as a global community on this.
Yes, Mike.
Yeah, so it seems like one of the key goals for the summit was to come up with this vision for a computational system. And I think John and other people have done a really good job of looking at, what does it require in terms of memory bandwidth, memory capacity. But I think probably an even more important goal is looking at what do we want to be able to do beyond the science, or what do we want to do from the output of the science? So how can we take the data that's produced by the computational system and really make it broadly usable? And then how do we also enable as many constituents to be able to use the computational system as possible? So I think in addition to sort of looking at what are the speeds and feeds, we also need to be looking at overall capabilities, and a lot of that will likely be software driven.
Yeah. I guess, yes, speaking for the computational systems, we want to de-emphasize the computational system. The purpose of that was only to show that the tool was feasible, but not that that should be the focus. In fact, it really shouldn't be the focus. Even the models, it was really back to what is it that we want to apply these tools to accomplish? And let's try to get away from the computational system. I think we've only said, hey, we could do this. But aside from that we can do it, don't want to make that the focus.
So I kind of want to go back to the renewable energy theme. That made me think more kind of surface winds. How do we know that the model output for surface winds that we're going to use to design buildings, and then also for wind energy, are going to be accurate? So to that point, I'm wondering, should we kind of consider more, should we improve our observations, expand our network in order to create a more robust data set, and just so we can verify the results from our model in the future? I know we're trying to get results sooner rather than later, but this might be a point to think about just to improve the model in the future in the long term.
And similar point was made by Haley Fowler regarding precipitation in the observational network.
I was just going to encourage us to think back about outcomes, but also embrace maybe a more engineering mindset. The goal here is to solve problems, right? And provide solutions in ways that are actionable by people who are not scientists, who are actually having to deal with the effects of climate and weather change. And if you come at it from that perspective, from an engineering perspective, you make those trade-offs about what is it we need to do to actually do this, not in hypothetical 20 years when we have better science, but on a reasonable timescale that actually can lead to some concrete outcomes. That drives you to think about this problem in a very different way, about the trade-offs, about what you do in computing, the trade-offs and what you do about models, and the trade-offs about how you engage the community, right? And if we don't want to fail, and wind up being isolated by a cacophony of disjoint voices, there needs to be a really simple story. And I think part of what we're trying to talk about here in terms of the breakouts is how do we coalesce these ideas into a small enough set of nuggets that there is some concrete direction that we can pursue. So just encourage you to think about that, lest we wind up having had a great conversation, but leave with no outcome.
Yeah, Dan, you said it very well. That's exactly right. There are a lot of boundary conditions to this in what's happening today. There's boundary conditions on climate models that are being developed, a lot of work that's being done. There's new technology, there's artificial intelligence, there's all kinds of tools and changes that enable what we need to be doing. But if we focus just on that, we miss the bigger picture of the goals that we're trying to achieve, and that is to provide useful information with greater fidelity, greater accuracy, reliability, less bias than ever before, and a step change, not just incremental work, but a step change. And I think we all agree, if you look at the literature and what I talked about yesterday in my opening talk, even those who feel like they say, well, we should be doing 10 kilometers versus 1, that's all based on computing capability. It's not based on the science. Everybody agrees that finer scales is better. It's a question of, can we do it? And I think we're about saying, yeah, we can do it. John's point is right. It's doable, folks. Okay, we'll kind of set that aside. Okay, then what science do we need to be doing? What developments do we need to make happen? What message? How do we build the community to make that happen? It's not about America versus EU and Destination Earth and Eve versus NCAR. It's not about any of that. It's about, if we don't come together and do something like the physics community learned how to do long ago, we're going to be right back here 10 years from now. And we will have let humanity down, not just society, we'll let humanity down. We can't let our own sort of, narrow interests overtake the importance of what we're trying to achieve very broadly. I think Dan said it very well. So when we go into these breakouts, yeah, we're going to have to roll up our sleeves and dig into some of the meat, but that's for us to do. Society counts on us to do that, but do it, as Dan said, through an engineering mindset of what are we trying to make happen, and don't lose sight of that. Those are all very important points. Okay, yeah, go ahead, sorry.
Yeah, no, I thought I'd come up to the mic since I work in a school of engineering and kind of think quite like an engineer, I think. Yeah, I think we just have the opportunity to do something transformational, don't we? We can see already that there's a massive step change in the science coming from these convection permitting modeling scales. But we can also see that actually society is adapting and making huge economic investments based on information that's incredibly biased and in a lot of cases just wrong, quite honestly. And it's not just for adaptation, it's for mitigation decisions as well. There's huge investments worldwide in net zero planning. There's huge investments in adaptation, right? You can make an economic case for this, I think, and I think you should do. I think it's something we've not talked about, probably because we're all scientists in the room. But actually, if we make these investment decisions and we build flood defenses or whatever it is that don't work, right? So we've done this in the UK. We built a flood defense for Carlisle. We added the uplift for climate change. It flooded again the next year, right? We're wrong about this stuff. We don't know what's coming as a society. We're seeing more and more of these 1 in 1,000-year events. We're seeing quite a few around the world this year. We can't just use past. I mean, I don't agree with one of the previous speakers who said we should be doing more work on the past climate in terms of the historic, I suppose, last 30 years or so. I think there's lots of reasons with extreme value distributions and statistics why actually we can't quantify the type of extremes that are possible in the climate we're living in now, never mind in 10 years' time. And actually we can make good economic arguments why this type of modeling system is needed to actually test. And the nice thing is, it's going to be really a really cool model, and we can use it to actually test a whole load of exciting things. And it's not just about, it's about decisions that society might want to make as well as some of the science as well. So we can, it's like a sort of, I guess a model that you can use to test assumptions I don't know what the right word, that isn't the right word, right? That's a science word. I think stakeholders maybe need to think about what the right words would be to use. But there's this exciting moment to do something that's actually going to make an economic difference as well, right? So we're not going to invest money into the sort of things that aren't going to work.
Thanks. Yeah. What Deanne is handing out here are the so-called challenge sets. If we, let me just bring up the slides real quick, tell you what these things are. And it may well be that we want to think about using these. Let's see. So basically, these are problem statements, they're scenarios. As Dan said, they're trade-offs, they're constraints and competing factors and so on. But the idea here is to come up with solutions, possible solutions and answers. And so there's 5 different ones that we created, and they kind of map a little bit to the breakout groups, but they don't have to. Again, this is flexible. The modeling, computational system, administration and governance, the funding, research and development, and building the international community with stakeholder engagement. What it strikes me that we could do here is to let the breakout groups go ahead and get together and decide what questions they want to address, and just let you figure it out on your own rather than spending more time here. And that the kind of the downside to that is we wouldn't have any cross-cutting questions where, say, 2 groups would be dealing with the same thing. But we do have a second session. So it might be the case, and again, I'd love to hear your thoughts on this, that we could go ahead and do the breakouts, get into our breakouts. And I think the 3 on the stakeholder engagement, AI and Earth system models and the computational system, they could kind of come up with their own sorts of, questions that are pretty obvious, but only a few, and really deep dive on them. And then the 2 cross-cutting, the ones that Dan and I are leading, could deal with some of the broader questions about, what is the mission and vision? What are we trying to do? How do we sell this? What's the story we're trying to tell? How do we think about this in messaging and engaging the community and governance? When I say governance, I'm not talking about an organization, but engaging the broad communities, we've heard multiple times, is very difficult. It's a very challenging thing to do, and we have to think about how to do it. And so, that's why Destiny and the folks from Japan and all these others getting together and say, okay, well, how do we do this? That's what I'd love to come away with, at least some ideas of how we can do that. And then, of course, there are folks that aren't here, and we can't leave them behind either. So we want to make sure that they feel like and they have a seat at the table, and that their input is important and received and used. So, but we didn't have infinite money to bring everybody here, and I think a huge group wouldn't have been as productive. So what do you think about that? Just having you all go into your breakout groups and come up with, say, a couple of questions. One that Chris mentioned, okay, what is the science agenda? That's a wonderful question for the breakout. Lay it out. Tell us what the science agenda is. And pick 1 or 2 or no more than 3 for sure, and go into those. Then this afternoon, you could continue that if you feel like, hey, we just didn't have enough time. Or it's like, hey, another one came up that we didn't think about. Then the afternoon breakout could be used for that as well. Barb just suggested to me, and I think it's a good idea, that we have a report out from the breakout. Maybe we could do the 11 to 12:30 and 12:30 to 1:15. Use that as a working lunch. Grab a lunch coming back from the breakout. Maybe finish the breakout about 11:20 or excuse me 12:20. Come back in, and while we're eating lunch, have some report outs. I think it's a really good idea. But how do you all feel about just going ahead and going into your breakouts and you figure it out? Figure out what the key questions are. You're the experts, right, in these different areas. Are you okay with that, at least to start with? Again, this is yours to do, so I don't want to inappropriately suggest we do something you're like, that's the dumbest idea in the world. Those of you know me, I do that a lot. I come up with really dumb ideas. Some things that even suck sometimes, according to John, but Dan, what do you think?
Yeah, I think that's probably a good plan.
Okay. Everybody good with that? Okay, well, you have this very colorful spreadsheet that lists which breakout you're in. And I would ask that you go ahead and go to that one to begin with. And then, like I said, people here have flexibility to move around. That's fine, but let's maybe get started this way. And then for the afternoon breakout, maybe there could be some switching around. Okay, so if you have any question, or if you don't find your name on there, let me know or let Deanne know. But these various rooms, the quad room is immediately across the hall. The other ones go down about 40 feet or so and turn to the left, and you'll find a whole row of rooms where those are located. We have the computer set up, their microphones. It will not be recorded because we just won't do that. It's difficult. Any question about the breakouts, what we're trying to achieve? You're going to come together, come up with your couple questions. There are flip charts in there for the scribe to capture notes. Francina also on the, you've got Google Docs, right? So there are Google Docs that are, those are on the website, right? So on the website, there are Google Docs for each of the 5 breakout sessions. You can log into your computer and put comments in the Google Docs as well. So feel free to do that. Okay, so we will come and get you about 12:15 or so, 12:20 to grab lunch and come back in for a report out. Guys, thank you, thank you, thank you, thank you. I love the discussion. We're all a good, friendly community, and these tough questions you're asking are really important. So thank you for your patience, and we'll see you soon.
So.
what does it take to explore the idea? I mean, to the extent that you buy into the idea that there is really that's quantum leap and resolution. It's better to go from 25 to 3 kilometers, 10 kilometers. Well, no, Tapia is not convinced, but okay, but I think we in this meeting.
The part inside, that's the biggest actual specialized architecture versus the degree. What if you take the what if you take the hardware frontier, but instead of trying to make a general purpose computer, just use off-the-shelf architecture, but try to optimize it to run climate models, and not just a single. I mean, the ratios to some degree. That.
Let's also try to.
Spoke architecture.
Well, so that was the whole question that I was trying to bring up.
I came in late, sorry.
Yeah, but I mean, the question is to what extent do we need a dedicated climate computer? Basically, Calvin was very clear we had not to debate.
Well.
Interesting. Sorry, I came in late too.
Yeah, he did not want to do that.
Which seems like
yeah.
But the question is like, how much better would a dedicated quantum computer actually, climate computer actually?
Well, I think you could, we have the best person in the world to answer that question, which is Misaki down there, who actually has a dedicated computer. I mean, I guess it's not a dedicated climate computer, but it's pretty close. And it's pushing it.
Problem with having a conference is people know you're in town.
Exactly. Twice as hard.
Well, it's more like, should I cancel my class?
Yeah.
For this, and I decided no.
That's really hard, I agree.
Already have traveled.
Yeah.
You're not teaching anymore.
No, I'm not.
Are you enjoying that?
Well, I would miss it if I had infinite time to do it, but the problem with teaching is that always I think it doesn't matter everything else. And so from that point of view, I probably will contribute. Yeah, and so I think there's a certain set of questions.
I mean, I took it as we're just gonna start early, just.
So we're a pretty small group, I think, so. Who wants to jump in and offer an opinion?
And then I try and look at the requirements and design a system based upon those. So there's some things that will come out of that. So there's some various things to look at. So there's obviously the physics-based models. There's the AI-based models that we need to understand the requirements for. There's the data products that are needed for some of the integration and presentation. So all of these things are things that we think need to be looked at, understand the questions that are involved, and then try to find the solutions, because we don't necessarily have all the data. And as is reflected at the bottom, right, there are a bunch of unanswered questions. I think another one here is things like AI resource requirements. We understand the simulation requirements fairly well. Do we really understand the AI resource requirements? So I'm not going to read through this, but I think one other thing that I will show just briefly, this is Peter provided this, Messer provided this as an architecture that you can consider hierarchical if you turn 90 degrees, where you can see some of these actors that we just talked about. This is one manifestation. Is it the right manifestation? Well, it's an interesting model. It's a very good model. It may not be the exact accurate model that we're going to end up with or architecture we're going to end up with to do this, but it gives us something to think about and reason about.
What is that?
So it's so you have the end user on the left, trying to get at the information, the distilled information to make their decisions. In the middle is potentially a data federation interpretation layer that can then coordinate the information that's being generated by simulation, by AI, or by archival data, and then have that as a way to then present it to the essentially the end user. And Peter, I hope I did it justice. I don't see where you are in the room. Okay. Questions?
Yeah, question, please. Yeah, sure. Maybe it's for Peter, but could you go ahead? Question, maybe it's for Peter, maybe it's too early. Is it on now? Okay. Maybe it's for Peter. Maybe it's too early to say that. Is the intent that the effort being formulated here holds all of those, or there are external actors in this as well? Besides the end user stick figure on the left.
So yeah, I mean, if you look at, so here's really the list of actors that we have. So that diagram was focusing on what is delivered to that top actor, but there are definitely actors that have to work on the elements in the middle, if that's the question. Did I answer it?
Maybe. It's more, can you put a dashed line around that shows what's part of what would be proposed in the funding model and what wouldn't be? And
So
does it include all those boxes?
I think it does include all those boxes to a large extent, but please, Peter and Irene, if
I was just going to say, didn't get into any depth of the notion of partners and flexibility of being able to interface. We haven't gotten to that level. So that
If I could just, yeah, maybe right, even though we have 3 boxes on the right-hand side, that doesn't mean there's only 3 boxes, right? So the simulation box, that means that's whatever, a simulations package as a service that's already deployed somewhere in the cloud. And that can be for every single model that everybody cares about, could be a separate box, or there could be multiple boxes for the same model for different configurations, whatever. And I think especially for friends Jupyter side, right, on the archive data, for instance, or on external data sources, again, that's not just one type of archive that we're interfacing with, but rather that means there are boxes, sources of information that from the outside get pulled into this climate information system.
And John, just want to say before you go, and right, so Peter mentioned, right, it could be multiple models. We know we have challenges there in terms of multiple models. Is there a way to do unification? That's an open question, right? But we haven't answered. And so that we're not trying to represent that explicitly. But I think to Peter's point, this is supposed to be more of a generic representation, a high level representation of what is possible.
And so we'd, as a pre-summit exercise, we'd worked out, the the requirements, or we'd gotten from the ESM people, the requirements for a high resolution kilometer scale climate modeling system. But in this discussion, we discovered that's only that one little box up in the upper right-hand corner there. And, you know, the practitioners are really interested in the data product, the information. And in order to figure out what we really need in these other boxes, we got to work it backwards from a story, a documented story about what is the end data product that they're looking for in order to suss out the requirements for all those other boxes that's really the system. So, you know, it's great, you know, kilometer scale computer is one thing, but this whole thing has to work out. We need those stories, those anecdotes, and we need to turn them into models. Use cases. That's the use cases.
Yep. Great. Thank you.
That's still up there, right? So we all have the stuff in the Google Doc. It is in there, yeah. Okay, I'll pull it up for you to make sure. I think it's there. Okay, it's not going back. Let's see here. Where is it? Francina, I'm stuck. Yeah, but, oh, is it maybe at the top of that? No? It's not going back.
You get to it from that.
From this one?
Yeah.
No.
Go to breakout.
Oh, I see. Okay, yeah, I'm sorry, right.
Oh, breakout Google Docs.
There we go. There we go.
Kill this.
Yeah. Okay, breakout Google Docs. Oh, God. It's already, I thought it was already there. Okay, I thought it was already there. Summary breakout. Where is it? I don't see it.
Go back to
Crap, where'd it go?
I think it's
Breakout Google Docs.
No, you got it.
Where did it go?
I think
saved it
it's
to the
here.
desktop.
Where is it?
Yeah. Oh, okay.
It's group 2, right?
Yep. Awesome. Thanks. All right. Yeah. So we were a cross-cutting group, and I think we appropriately cut across a lot of different topics. I think, you know, one of the big organizing principles of what we were going through was trying to, let's just start. Okay. We have these high resolution models. Why are we building high resolution models? There's two obvious reasons. One is so that we'll make a better model and all of its predictions of everything will be better. And on the other hand, because the whole user community wants high resolution data, it wants information about stuff that can only be reasonably produced at high resolution, extreme winds, extreme forms of precipitation, hydrological forecasts, flooding, floodplains, you know, all that stuff needs high resolution output. And we're currently getting that from downscaling of low resolution models and from extrapolation from observation. So can we do that better? How can we do that better? How can we build constituencies for that? So what do we need? So we have a section, we have a long section here where we talk about like how to address the concerns of particular constituencies and who can we entrain and get excited about these capabilities. You know, the obvious agglomerators of risk are the reinsurance industry, of course, but there are lots of other large organizations, you know, Defense Department, cities, other disaster management communities who are exposed to the sort of the sum of all risks related to climate, and so have powerful incentives and maybe some resources to help with what we need.
let's see, there's a nice section in here somewhere, yeah. So we wanted to talk about validation. We want to talk about a little bit about governance, like how do we set out a program in advance that will be convincing to people that what we're going to do is going to be important and actionable. So that involves laying out validation pathways against observations that will convince people that first of all, that there's a need for improved forecasts. Like if we can go out and build a validation infrastructure as a sort of topic zero and say, okay, well, here are the things, here's a sum of things that people care about. And of course, there's a lot of literature to be consulted on this too. Here's a sum of things that people care about. And here is our ability to actually address those concerns on the basis of the current mix of historical reanalysis plus forward-looking climate models. Then we have that as a promised infrastructure with which to address future the new models that come out of this, so we can demonstrate improvement in some kind of a stepwise way. And in terms of targets for validation of things that are of great concern and currently very difficult to pull out of climate models, that would include things like wildfire risk, flooding, and extreme weather impacts. We had a bit of a side sort of tangential conversation about sea level rise and what is it about a high resolution model that might actually talk about this. A few of us were wondering whether we need some additional we haven't heard from any like ice modelers in here, and that's sort of a different set of talents and probably a different set of computational problems than we've been addressing in terms of as we've thought about 1 kilometer atmosphere modeling. But of course, it's one of the major determinants of the risks, of one of the major uncertainties of risk and exposure going forward. And a lot of that comes from dynamics that aren't only arising from the atmosphere or atmosphere-ocean coupling, but also arise from ice sheets and their physics. Let's see what else. Yeah, so I think, I don't know, Jim or Don or Dan, am I leaving out major topics? We wanted to talk about building constituencies and how do we sort of get out of some of the political difficulties of addressing climate change. And one of the things that occurred to us was to talk about ability of these models to really address in depth natural climate variability, since often that's, people want to say, well, but what about natural variability? How do we know that this, and of course there's a lot of literature on that, but maybe a very capacious high resolution modeling approach that could demonstrate very good skill against past time series of climate variability would enable us to do better outreach to people who might otherwise be concerned, let people who feel that the ratio of that climate scientists don't sort of undervalue natural variability to maybe address some of those concerns. Jim?
I guess I would just simply say that what drove this a lot was the need to identify constituency, and identifying that constituency. So, for example, the U.S. Navy, they would be very concerned about things like sea level rise. That identifies a problem that we can use, one could use to be focused on, that would help focus the effort and also refocus a way of evaluating how this thing is building. So the idea is, let's find out who would be interested in these capabilities. We know how to run models at the kilometer scale on a global basis. We know what the benefits are. We also know that there are systematic biases that need to be sorted out if you're going to convince anybody that the data you're getting is any good. But that was the main point of this discussion, I think, the driver.
Any other questions or comments? No. All right. Thank you. Oh, well, Dan.
Well, I just add to that. I mean, to amplify what you said, Dan, and what Jim said, focusing on a small number of compelling drivers and working backward from those to say, what do we need to do to address solutions to those problems, right? And it's focused, but it starts with those stakeholders and convincing evidence that you can solve a problem that really matters to them.
Yeah. Okay. Thank you. Three. Let's see if I can. Oh. There we go.
These are mine, right under yours. Anyway, I will try to impose some structure on the broad discussion. I think there was a few themes. I mean, the overall theme of the group was Earth system modeling and AI. It was kind of everything. So we talked about the benefits of kilometer scale resolution. First of all, whenever we talk about kilometer scale resolution here, we have talked about the atmosphere. There was even some sort of implication that the ocean is trivial, and it's not. And ice sheets were just mentioned. They're also important. I think depending on what we want to do, the rest of the Earth system also deserves attention. And if our focus is on timescales of decades, it deserves as much attention as the atmosphere. Kilometer scale modeling is helpful and is crucial for monitoring data assimilation, for having a unified approach from weather to climate prediction. And I think NICAM is one example where that is practiced. The general sense in the group was that we will need a hierarchy of models, and the hierarchy of models is not necessarily different models, but ideally one model that you can run from LES resolutions all the way to Corsa resolutions, and then run it at higher resolutions, say even LES locally to train Corsa resolutions simulations, or run at kilometer scale resolution for shorter times, use the output to inform Corsa resolutions. And what you want is a model that works seamlessly across scales. And of course, the reality is, NICAM has been doing this for decades. MPAS at NCAR does provide that capability. SCREAM at DOE does. The CLIMA model runs from LES to global scale. All of these models are already doing that. There's considerable question of what you may not get from kilometer scale resolution alone. And one example that came up a few times is the recent trend in Pacific, equatorial Pacific temperatures that's not produced by any climate model accurately. And there's a question of why that is. There is evidence that this has to do with feedbacks going back to the Southern Ocean and mixing in the Southern Ocean. So that would be evidence that you also need higher ocean resolution, and not just higher resolution on the ocean, so say resolve the mesoscale, but also better parameterizations of upper ocean mixing in the Southern Ocean that's ultimately responsible for subducting buoyancy anomalies and the like. And if you're worried about societal implications, ice sheets clearly are very important. How warm water gets under an ice shelf, that seems to be a key factor for destabilizing ice sheets these days, requires high resolution and improved modeling of the physics of the coupling between oceans and ice sheets and in turn ice shelves. There are clear benefits to resolution somewhere here in ice sheet modeling as well. And this is an area that's quite under-resourced. A typical ice sheet model is developed by one person somewhere. I think it would benefit from investment there as well. And there's only a few ice sheet models around to begin with. Clearly, kilometer scale in the atmosphere can improve the representation of convective processes, precipitation processes, mountain hydrology, high latitude processes. For example, the coupling to ice sheets was one of them, same point again. Yet just going to kilometer scales alone is not necessarily sufficient. For example, ICANN at 5 kilometer resolution has larger RMS errors in precipitation than the median of 6 models. Just the resolution alone is not gonna be the panacea here. We talked a bit about vertical resolution, likewise something that isn't discussed much. there's potentially large benefits to increasing vertical resolution, especially in the lower atmosphere, representing boundary layer clouds. And the nice thing is the compute cost of vertical resolution is only linear in resolution, so it's for less costly than increasing horizontal resolution, where the cost is cubic. And even if you go to kilometer scales, we still need to represent boundary layer clouds, microphysics, aerosols, and the like. Resolution may help, but it's not going to be solving the issues alone. We talked about code a bit, and I think one discussion point was, wouldn't it be nice if you have a code base that's open and flexible enough that you can experiment broadly, including with whatever AI tools you want to put in there, learning about some processes or all sorts of processes among Go. If you have a code base that enables that, that would clearly accelerate progress rapidly. To assess how well we do, so if you want to accelerate process, you need to measure against something. We have robust evaluation tools, the ECMVal tool, that is used to generate the IPCC scorecards. For various other model components, there's ILAM, for example, for land models. That's quite comprehensive. These tools are around. They're not all that widely known outside the climate modeling community. They deserve to be widely known. But I think there was a general sense that those types of evaluations is what we need. They were helpful. A fair bit of discussion about what to do with data. If you do kilometer scale modeling, or even at 10 kilometers, the problem is essentially the same. You generate a lot of data. You want to be able to analyze the data. And ideally, this would be all happening somewhere in the cloud, that you analyze the data in the cloud. The data would be stored in the cloud. The catch is that, for example, 100 petabyte of storage in the cloud at current commercial rates cost about $1 million per month. So that's quickly prohibitive. Maybe there's a space for public-private partnerships. It is something government agencies could take on. DOE could build a facility for data storage and access. The key thing is, once you're talking about tens of petabyte data sets, you can't move the data over the internet. So you need to figure out some way. I can tell you what we have done sometimes in my group. We sent a grad student with a tape drive or a disk drive on an airplane to get the data, but that doesn't scale so well. So you need to put the data somewhere where people can analyze it, but ideally also have the storage where the data generation happens. Some discussions about training AI models, emulators on the fly. I mean, in the end, the data fire hose, Chris called it, requires that we build emulators as a form of data compression or other data compression tools. But at some point, you'll need to store the data probably to train these models, or at least we don't know how to do this on the fly. So that's a challenge where I don't think we had the solution. I think there was also a general sense that we need open access to whatever high performance computing system comes around, open in the sense that it's open to modeling groups broadly. Fair bit of discussions about code. It comes again on language. I think the essence of it, whatever you do, it should be future-proof for GPUs, whatever might come after MPUs, which requires careful consideration of the code structure and some thought about languages. Workforce, not much discussion, just brief statements. So universities can attract early career scientists, which is great. They love to work in this area at the intersection of AI, computing, and climate. That's one boon for doing climate modeling in the university setting. But a challenge is that you need career paths for staff, software engineers, and the like. That's difficult to achieve in a university setting. They have clear career perspectives, adequate compensation, and the like. And then for people who graduate right now, there aren't really jobs in climate modeling, or not many. There's the finance industry, there's a risk industry that takes on graduates, but not directly, say, in people experienced in climate modeling. The discussion of whether we should have one model that rules it all or multiple models, it was brief and clear. One unified model is not achievable. It's not realistic. We'll have multiple models. And even if you build this central compute system, you can build the model there, but it should still be open to other models. And I think for competition among models. The language choice is somewhat important. Fortran is a good language. It's prevalent in climate modeling. but it's really unappealing to early career scientists right now. So I think, Kelvin, you started out with saying, well, you don't want to rewrite. That kind of puts you in the realm of you're kind of stuck with Fortran. But I think it comes with significant risks. It's a risk in attracting early career scientists. And also, you have to realize that it's really challenging to integrate AI tools in Fortran code. It's a major bottleneck in many projects I've seen. And yet converting existing codes to other languages, so right now the choice might be accelerated Python. That's in itself a significant undertaking. Dave said they estimated for CSM, it would take 100 person years to do that. But then adapting existing code is also a significant undertaking. It's not clear actually that this is more work than adapting existing code. Yeah, and again, I think the AI question, the open source packages we have, PyTorch, TensorFlow, and the like, they have driven progress in AI, and they offer obvious benefits for system model development. So you want to be able to interact with that ecosystem efficiently. And that's something to think about when you think about languages to use and the like. Of course, you can do anything in Fortran. People always say that it's possible, but it's hard, and it's something you want to think about. I think, I don't know if folks, Chris and Stefan, Dave, Maria, want to add anything else here? Andy?
One or 2 points. So one other discussion that we had was on, what's the appropriate timescale of application of these models. So obviously, kilometer scale models are very expensive to run, and there's actually, I think, a surprising amount of interest in doing runs which are basically a decade long. So are really aimed at short range climate variability. From the science point of view, the use cases for those are to sort of identify the range of extreme events that are likely in the short range. And also, there are certain forms of climate variability that are very interesting. One of them right now is the so-called pattern effect of SST, where we tend to have got stuck in a little bit of a permanent La Nina state. And there are hypotheses about what's causing that, whether we're likely to get out of that sooner or later. And kilometer scale coupled modeling would be a potential new tack for looking at that question. But there are 2 corollaries to this. One of them is, if we're going to do modeling on that scale as opposed to 25 to 50 kilometers, it is partly an initial value problem. You have to address the issue of coupled data assimilation at these scales. And another one is the fact that then there is a competing AI-based approach, which is basically based on using historical data to create an ML forecast model, which can forecast out to the level of generalization needed over the next decade. And so Stefan's method, Stefan's group, the neural VCM approach, is potentially a good vector along that direction, but we need a couple version of it to really realize that vision.
I have a question, if I might. In our group, we discussed a lot about what the models actually would be. And you mentioned vertical resolution. So my question is, do you talk about how high the atmosphere needs to be? Do we need to resolve the stratosphere for like geoengineering kind of applications? And even more directly, do you think we need to have atmospheric chemistry models included? All this would make would have serious impacts on what the computational requirements are.
No, we didn't really talk about it. I mean, my own take is, yes, you need a stratosphere if you want to be serious about climate modeling. Don't need terribly high vertical resolution there. So a number of levels, it doesn't need to be high. And chemistry, that's actually a difficult one. I mean, clearly we need to be able to model aerosol indirect effects. I mean, this is one of the big unknowns in the climate system. The question is, how much chemistry do you need to model that well? And I think that's open.
I think the point about a unified model is a really interesting one. And I guess my question is, what trade-offs do you see in terms of having the ability for lots of different models to run on a machine, and presumably none of them very optimally? I mean, we see what the performance is now, we're trading that off against maybe much, much higher performance for a framework that involves a couple of die cores and multiple physics packages to be run much, much faster to do maybe, 20 years instead of 10 or whatever. Did you talk about that? I'm just curious because I see the arguments, but I'm just wondering, does that leave us sort of where we're at today? Because that's kind of what we do now versus some other alternative.
What we talked about in a group is that just the saying one model for all, it's just simply unrealistic. And then Mark Taylor and Andreas and I had a sidebar conversation. I don't see Mark right now.
So do you literally mean one model, like one die core and one microphysics and one, or a framework that has multiple die cores and stuff? I just want to be clear what we're talking about when we say a model. Are you really saying it's one model or one model that has multiple pieces?
Even one framework. I mean, let me just say what
Okay.
Mark and I don't, is Mark here? There's Mark. We talked a bit about it just before lunch, and actually just with Andreas, we were comparing Torsten actually. We're comparing performance of the various models we have around. And I mean, the interesting thing is the E3SM icon, according to Mark's extrapolations of limited data and Klima models, the performance is, within order of one factors all the same, which is to say, yes, I mean, and probably the same will be true for MPAS. And I mean, there are things you can do with tailoring performance to architectures, and we have all done our homework to harvest the low-hanging fruits. But in the end, I'm not sure you are getting to orders of magnitude there and differences.
Yeah, I think that I think the Torsten's point was that there are differences that are unlikely to be able to be converted into a single code base. They are using the same language right now, but on the other hand, with back-end software engineering, make them all somewhat performant if the hardware. And in fact, the better strategy is not to say, okay, we're going to have one model or one code base, but just to specify the hardware based on some best guesses and what's going to work, and then everyone else has to get their stuff to work on that, and you offer them help in making it perform.
So we're basically, I mean, let me be crude and say we're basically giving in and saying we're fine with 4% of machine capability, right?
No, that's not that bad.
No. But I don't think it's a whole lot more than that, is it?
Well, no. I think, I mean, Mark, do you want to say something about it? It's the codes are pretty efficient. You're hitting memory bandwidth limitations, but there's nothing you can do about that. But they're efficient other than that.
Yeah, I'm just trying to learn. Yeah.
I was going to poke at the same thing though from a different angle. So, model becomes synonymous with the code base. But we had an experiment 30 years ago in astrophysics where we agreed to a common code base into which we plugged different models in order to do comparative analysis. And you get to reuse the build system, which is a real pain in the ass. It's very easy actually to do mixed language if you have if you have a code base that invokes these things as modules. You don't have to choose which language by going with that. And you get to reuse the IO subsystem, which is another real pain in the butt. So is there any utility in having a framework into which you could plug multiple models, and thereby you don't have to have a separate harness then to get the data products out for that matter?
This has been discussed since I've been entered the field 30 years ago. There's the Earth system modeling framework, which by now is obsolete, I would say. It has always been the wish, but I think the reality is, especially with climate, there are national interests. Different countries will want their own climate model. That alone will make this a lot harder than the astrophysics problem, I suspect. But more unification would be nice. Right now, it's going away from that, and that there is a greater, which I think is good. There's more experimentation with frameworks, with languages, and the like.
Just to go back to this 2% of peak.
Not peak.
Right. I think on today's hardware, today's models do horribly poor in terms of percent of peak. But on the machine that John talked about yesterday, I'd say most of the models are quite similar, and they're all going to benefit, and they're all going to run. We're talking about factors of 2 on that new hardware, not factors of 10.
Well, I mean, depending on whether you had a chemistry package or not, you could always balance things so that you get 100% of peak flops, but the peak it's really a question of what are you limited by? So are we maxing out the memory? Are we maxing out the flops? Well, with the DMA and no chemistry, we were able to get like nearly 100% of peak on that. But peak is, number of flops. But that's, I guess I worry about using the term peak. Because
I agree. I mean, if you want to maximize that, lower the resolution, right? Have more arithmetic intensity per GPU. That's very easy.
It's throwing away, flops is cutting off your nose to spite your face. If they're there, then so what? Didn't use them. It's not the most expensive thing in a machine today. The flop is not the most expensive thing.
Yeah.
But we engineered those out to make room for cache, which is a good trade-off. Well, you could, but economics will dictate whether or not the rest of the market will want you to.
Okay, that's it. Thanks.
Thank you.
I put it on a slide already. Yeah. I can find them. Let's see if I can find them. Where? In what? On the desktop? Ah, here. How do I go to it? My Mac fingers don't work. Okay, here we go. Is it Control C on a Windows machine? Back to the browser. All right. I don't consider these final, but I thought it was easier to capture the summary. If I'm going to talk about 3 themes that I think we mostly paralleled or crossed over at various times, but kept returning to. And with apologies to the group, this is of course in my words, which means my lens to some extent, but I trying to be captured here. So the first thing that came out, and I think we returned to it a few times, is trust. We've seen that in a few of the other comments so far, but from a stakeholder or a practitioner point of view, without definition of what that is, it's really what can we believe and what should we not believe? And there are many implications. And so we talked about several different ways that we can get trust, what might be possible, what might not be possible, but also how that fits into the ecosystem. It's a question that relates to the scientific motivation, some of the scientific motivations, which is do large and regional scale trends drive many aspects of trust? I can think of ways they do. I can think of ways they might not. The high resolution component itself, whatever that ends up being. I think for this group here, because the trust is so important, that places a burden on this group to show that that's useful if it's going to be supplied outside of this, right? Outside of, broadly out there for the world. So something to keep in mind. And then, the discussion of what do we care about in climate? I mean, statistics of events or parameter thresholds through the historical simulations, right? Many of the things that have come up in these conversations. Another part of trust here is translators, climate translators. So people who know how to understand and interpret what you can trust, what you can't trust, and communicate to one class of stakeholders, which is the end consumer making decisions, right? That expertise very often doesn't lie at that level. And then of course, biases we'll still have, right? That's come up many times here. How much do those matter in terms of our trust? There would be people out there trying to poke holes in this, no matter how good it is. How much does it matter for my decision or my client's decision or my customer's decision? We talked a bit about output because there's a lot of talk about democratization of data and just making it available, which is all very useful to the extent it can be done. And I think back to the comments I just made ago, even in summary form, it sort of requires expert users in a lot of cases to access it, right? So just putting the volume possibilities aside, you just have to know what you're getting and what it means to you. And not everybody is in a position to do that. But there are use cases for it. And one core use case is answering hard scientific questions, right? So we have to remember that is a use case, that is a stakeholder group. Many of you are in that room, and there will be a large scientific community out there dealing with that. But there are a lot of others that can't. And so we always want to be thinking about empowering the ecosystem. And many of us in that room, we're sort of in that ecosystem. We might not be the one making those final decisions, but we're helping other people make decisions or figure out how to use information to make decisions. So one thought, where does that lead to places that the computational system and ancillary storage does not have to support something, right? I think very quickly we'll be getting into that situation because we can't do everything. But more practically, what output do we need to save to drive downstream modeling? So we came up with sort of 4 types of output classes, if you will, that map in some ways, in my mind, and I think this is the way we talked about it, into stakeholder groups or classes, or maybe use case groups or classes. I think those are almost interchangeable often. One of them I already talked about, which is scientists who are doing analysis and answering scientific questions. That's a clear use case. There are others that would be capable. There's banks of consultants out there that go access raw climate data and answer specific questions for industry use cases. But there are other kinds too, right? What do we need to save? And they're a different structure, right? They're a different structure formally. The beauty is in this world, they're all structure of some kind. So storage, you can kind of map this out, what this looks like. But we have an output class that would be for, say, dynamic and statistical downscaling. There's an output class that would be for doing extreme events, extreme event calculations, extreme event fitting, or stochastic event modeling, which sometimes are very close to each other. And then there's another class that might be machine learning experimentation and model training, right? Those output banks might look different, which may open some opportunities for how we think about dealing with output. And I'll just add again my own comment that I think the space is too vast to make it the problem of this project to drive it. I mean, I think a data explorer is one thing. People be able to discover data is one thing, but there's no small set of UI or UX that can really drive a wide set of use cases in this world. It's just way too big. And the other topic we talked about a bit is time length. And I think the general consensus came to be, we don't want to be too constrained in this. Even in our room, we were a biased set of stakeholders, right? Middle to end user types that don't cover nearly all the use cases that are out there that we even knew about, right? So some examples of these might not be accurate, but this is how they were written in the notes, so I borrowed them. I think they're close enough for discussion now. 5 to 10 years is sort of the wheelhouse of insurance and agriculture, for example. For big capital investments, both for municipalities, but also in the private sector, it's sort of 10 to 50 years, right? They're looking at building lifetimes that are way out there. Systemic risk, which some banks worry about already, that's a long time problem, right? That's market collapses and those sorts of things, because you can't say when it's going to happen. So there's a lot of room here. I don't think we want to be in the business at this point of saying, well, we're going to do 10 years, we're going to do 30 years, let's do as much as we can, right? Let's go out there. And again, if you think about it, if this maps at all, I think to the output that we just talked about and different groups and use cases, maybe there's a way to kind of simplify some output classes and even thinking about hierarchical modeling, like we just heard about. So I think it intersects things we've heard in a few places, but that's what we've covered so far, and I will refine these if we get the opportunity to. Hopefully I captured fairly the group discussion.
Thanks, Josh. Any questions?
One point that we discussed too is just variables and what kind of variables to track. And we looked at that Kona score of 4 as a potential starting point. I don't know if that was captured there, or if that's worth sharing with this group at all.
Yeah, that was underneath. I took it up a level from that, but that's sort of buried in here. That's one class, which I think that particular one we looked at maps mostly to direct model output use cases, and those are 2D fields, right? So there's a structure to them. Maybe they're not all 2D fields, but all of them I saw on the list in 15 seconds were 2D. So that was sort of my input, my suggestion, that you can take these sets of use cases and possibly map them to output sets, if you will, right? Which is just a list of variables that then somebody who knows how to do it can go get that information. Yeah. Sorry if that wasn't clear, Gene, but it was in there underneath. Yeah.
It's kind of part question, part comment. I think the timescales that you've talked about are the timescales that people are making decisions on. But I'm not quite sure how close that correlates to what you need to run. So because people are making a timescale on as let's say a 5 to 10 year or 0 to 10 year timescale, if we're interested in understanding their decisions, then we might need to be, understanding natural variability, climate change variability, and things on those timescales. And therefore, the simulations might not necessarily be that, or just a big ensemble of that even, but might need to be other kinds of simulations.
Yeah, no, I completely agree. Yeah.
Great, thanks, Josh. Well, we're going to rejigger the agenda a little bit. Deanne, I don't know if you came in. So what I suggest we do is for the next half hour from 2 to 2:30, and I'll put up on a slide here the new structure, and I haven't talked to the planning committee yet, but 2 to 2:30, let's have a break, and I'd like to have the planning committee kind of huddle over here in the corner, and then have another breakout from 2:30 to 4, where we I've got some other topics that I think relate with the challenge sets, but we don't have to do those exactly. Again, I think we sort of do this on the fly. And then we have a report out from 4 to 5, and we finish about a half an hour early. But I'd like to talk to the planning committee to just, make sure we're all on the same page. But for right now, 2 to 2:30, a break. Come back in at 2:30. We'll tell you what's going on, and then probably another session from 2:30 to 4, another breakout that'll hit both the breakout and the challenge sets all in one fell swoop, and then a report out from 4 to 5, and then that'll be it for the day. So anyway, if you would go ahead and enjoy the break. I don't know. Do we have refreshments already? They're already here, right? Or it's kind of okay. So Deanne will check on that to see if we could sort of accelerate whatever they were planning on bringing out, because we're upending things just a little bit. And then we'll call everybody back just to reset, okay? So half an hour, a break, and then we'll be back at 2:30. where we're headed this afternoon. So what we're going to do is, as I said, from 2:30 to 4, we're going to have another set of breakouts, but they're going to be different than what we had on the agenda originally. So we're going to only do three breakouts. So only be using 3 rooms. The first 2 groups, groups 1 and 2, the crosscuts are going to go into these other groups if there's room in the room. But here's how it's going to roll out. We're going to ask the folks that were in group 5, which is the original quote stakeholder group, to develop a bunch of use cases. Just come up with them. They don't have to be long. They can be a sentence or 2. Come up with as many as you can and think broadly about all stakeholder communities, the stakeholders, across the board, including researchers. We'll have researchers in there as well. We'd like group number 3, which is the original machine learning, AI, and Earth system model group, to come up with the R&D agenda. What is the R&D agenda? Let's come up with an R&D agenda. And data and tools group number 4, which was the computing systems group, to come up with a deeper dive on data and tools, all kinds of issues associated with data. I personally don't use the term data for model output. I think of data as observations and collected data, measured data, and output as output, but I think we're all saying data is everything, okay? And that's perfectly fine. I just don't want people to get confused. So the tools, the translational tools, the things that are needed to take model output into other formats and things like that, decision support tools, things like catastrophe models and things. What do we need to be thinking about in terms of data, transmission, transportation data? Tapio told us, rightly so, that you get these huge data sets, you can't move them around. So how do we do that? How is that dealt with? So is that clear to everyone? The group 5 originally, which is the stakeholder group, you're now going to be writing use cases. That ought to be kind of fun, I think, actually. The R&D agenda, Chris had kind of mentioned this, group number 3. See challenge set number 4. That was something that we wrote down with rather careful wording to talk about what the R&D agenda, what we mean by that. So it's up to you to kind of frame it. And then the data and tools group number 4. In the same rooms, again, in groups 5, 3, and 4 were in before. And if you need to, well, just look on your sheet or I can tell you what those are. So any question about that? We'll do that until 4. We'll come back and have kind of report out for an hour, and we'll let you go a half an hour early. In fact, I think supposedly we only have this room until 5 anyway, right, Deanne? So this will make the hotel happy. Okay, but I think we'll be good by 5. So any question about that? Or is that clear? And then we'll again have these report outs, and that'll be really wonderful to hear these. So good to go? All right, cool. Well, yeah. I'm sorry? The same ones. Group 5 goes into its room, group 3 into its room, group 4 into its room. The ones they were originally in. I can tell you what they are if you don't know. Group 3 is in, the R&D agenda is in the quad room. Group 5, the use cases is in the loyalty room, and group 4 is in the excellence room. Go team. So we can go into just wherever we want to go. Pick your favorite poison there. There weren't many people in there, and This is group 3. Group 4 is ready? Okay, group 4. All right. All right.
Kelvin, does anybody? Oh, I just,
That's a slide.
you're saying right there. That's what you're saying. Okay. That works. No, that's not the right figure. Yeah, we'll get there. We'll get there. All right, here we are. And of course, we have to have another figure. Let's see. Can I make it a little smaller? Will that work? No. Oh, this will work.
Oh, yeah, there you go. Do that.
Yeah, I got it. Just gonna drop it a little bit. Is that almost enough? Let's see. No, don't do that. You need stickman. All right, I'll bring it down a little further. Okay. All right. So this is what we did. Thank you very much. Okay. So you can see here what we have is the end user at the top with a bunch of potential use cases going across there. And then we have this data info, the ability to take whatever's being produced by those things below in our previous diagram, whether it's archival data, simulation, AI. And what we're going to talk about is what are the issues with this picture? We're obvious, this is really just set us some context. It isn't the result of our discussion. Okay, so, and stop. How did you know? Very good. Okay, so now we're going to go back to the bigger size. Okay. So as we've been saying all along, right, we recognize this all needs to be use case driven. We'll get a report out from the other team that's going to help us with these use cases. And so that can clearly refine what we're talking about here. So we kept it more generic. So we started going into what are some of these generic requirements that we need to deal with when we're talking about this layer to basically interpret the data to make it usable for our ultimate end users. So there are concerns in a bunch of areas. What are the reproducibility requirements? In some places, they're very strict. In other places, they aren't. And this has been a real challenge in weather and climate. Part of that is maybe, can you replace it, as has been done in other areas, with uncertainty quantification rather than strict bitwise reproducibility? There's the provenance and curation of the data, and potentially the software and tools as well. So chain of trust can be very important for both data and tools. Can you trust it? Explainability. So you may have some differences, whether for various reasons that you may have differences, whether it's changes in data, changes in tools, other types of issues. Can you explain it? Is it better? Are there things, this is something we would like to be able to do. There's the time frame, time scale. This is not time scale, it's time frame in terms of needing the response. When you are doing, when you are the end user, how quick do you need an answer? And so this can be dealt with in some ways with quality of service. That may not be a panacea, but it's certainly something we think is going to be important. Who has the rights to access the data? How do we control that? Well, the most general way is to use some form of ABAC, attribute-based access control. For those familiar with role-based access control, that's a subset. A role is an attribute. It's just one of several attributes. And we realize that we really need to have some lighthouse use cases, hopefully based upon other discussions that will help us really tease out the specifics in these requirements. So once you have requirements, then you look at optimization. So there's a lot of different optimizations you can talk about, co-location, dealing with latencies, dealing with bandwidth issues, dealing with computational issues. They're in many ways second order to the requirements, but just how much so, right? Does this really get to the point where if you don't meet some of the optimization concerns, are you really failing? in some of the requirements. And then there's also this issue as you're doing these optimizations. When we talked about that hierarchy, we split apart the idea that you have these domain scientists, the people who do the climate prediction and the models, versus the computer science scientists who would help with the implementations and deployments. Is that really a necessary strict separation, or are there ways to blur that line? And we had some claims that, well, maybe there are some strategies to blur that line to help with optimization, to allow the domain scientists to more quickly experiment with better methods. And so again, this is something that we want to be able to do when we're investigating these kinds of tools. The next big area we looked at is, well, what really is the target here? Are we really looking at only targeting a federation or a collaboration of specific partners, or is this really supposed to be open for everyone? And the reality is that there's deep concerns about equity. And I think this was in some of the pre-read materials about parts of the world that see the most consequences from this kinds of, from environmental and climate kinds of things that don't necessarily have the access or the money to be developing all of these tools. And so the feeling in the group was that we really need to keep these thoughts in mind as we're making choices, because there are impediments sometimes depending upon those decisions. An example was given of some data sources may say that you can't give away the results of using that data for free. And so what do you do about that? Well, maybe you decide you're going to have to look at some alternatives. So again, I think this was considered something very important to be adopted by any future research. Any future projects. So then finally, we talked about some of the differences between doing research and providing operational production use for this. We want to be able to have both, but we have to recognize that, you know, when you're doing research, you may not want to be able, you may not be ready to commit to those results, and we have to have a way that can separate the two, but also have the agility to move to it when we're confident in it. All right, I think I got through it. Please, anybody in the team, if I've missed anything, feel free to add. Okay.
Questions? That was fantastic. Okay, how about which group wants to be next, R&D or the use cases? Who's doing it? Okay, all right. You have stuff is online, yeah, right?
Yes, but
Oh, okay.
Okay. So we started off by everybody taking a few minutes and writing down a bunch of their use cases to kick it off. And I think we established that there's lots of use cases. The one thing of various kinds, so they were sort of brought in at high level or sort of a more detailed level. Both kinds, I think, came up. And I guess the one comment that I'll add on top of that is, this is, you know, I think in some ways we're building urgent matters, you know, at a humanity level, right? Our view on use cases is extremely biased to North America and our particular problems of the day. So there's sort of a mismatch, and I think there's going to have to be just some thinking on the planning team or whoever's writing this proposal to about how to really pitch the urgency of it, right? I mean, that said, there are broad use cases in various sectors that we know about very well in the developed world, where most of us come from. And there's lots of ways to think about how to tell stories that link the two things to individual sectors, or, you know, whatever serves the purpose. I think in a sense that there's some storytelling here, and we have lots to draw from. The notes, there's a long list of use cases people brought up. One way we sort of, towards the end, circled in around a way to start building categories of this, right? There's going to be, for a lot of use cases, there's going to be a lot more work that has to happen from model output after it. Many of us work in downscaling, building synthetic events, extreme value analysis. These things are still going to be needed. most likely for the foreseeable future, certainly in the next 5 years. Okay, probably the next 10 years, maybe going further. So if we carve that off and just said there's a bunch of use cases that are going to need to be addressed by that, and ask what do we need to serve that purpose? That's one broad swath, versus a bunch of stuff that can be served more directly. That's another broad swath. And then I think a good part of the story here that came out again towards the end is part of this is asking what a new GCM can do to serve both of these, right? And I mean, one thing that's clear, this is an example, it's not the only one, is downscaling will improve if the GCM improve, right? In terms of becoming less biased. And that's all categories of downscaling. That follows to synthetic event generation in future climates. It follows to extreme value analysis in future climates. So I think there's a good value chain, sort of almost circular here, that there's just some things we know we're gonna have to do that aren't gonna be solved, that can't solve certain problems that the GCM has to solve, right? And that's one way to think about it going forward. So I'll leave it at that. I don't know if we answered any big questions, but we tried to get to some ways to think about it. So.
Do you have some of the example use cases? Are they accessible there? You know, or?
I think they're in here.
I said no, it might be good to show just a few. We have a lot. Let's just say a lot.
Here's some. So these are pretty. So there's a specific set here. Get rid of that. And these are sort of classic risk types of questions, energy driven in this case. There were some comments about time series, how to, again, energy driven use cases. Then there were some more policy driven things, water availability, more pressures on regions, water, which is of course a big thing that we know GCMs generally don't do very well. And again, anything that can be improved in there is going to help the sort of the downstream modeling, if you will. I asked, what does a bad year look like? That implies some spatio and temporal correlations or cascading events, something real but plausible but low probability. There's some urban planning use cases, sea level, and then there's a lot of, I don't know if these are all compound, but various kinds of combined and sequential events, bunch of stuff in here. So I don't know what the fate of this is all going to be, but that was my. Oh, you did? Oh, down. Oh, here we go. Okay. So I'm sure it's perfect. But yeah, I mean, I think we could do further work to try to bucket these in various ways. It also could be that there's a few compelling, or even within the buckets, ways to draw linkages, to tell stories, to sort of say, these are examples of urgencies we know about, but I do think there's other ones too, like driving climate migration and stuff like that we aren't prepared to address in that room. We weren't prepared to address it. So anyway, these are open, all available through the webpage, so anybody can take a look and add more.
We had specific stories that we told, like, okay, what is the likelihood, or what is the possible occurrence of tornadic environments over each county of Illinois for the next 30 years to use for the development of new policies and building codes. So we try to think in terms of practitioners and end users and why they need the information. We didn't say how it's going to happen. And this is this important interface between practitioners and end users and the community that's providing information. So this is kind of just a summary of terminology. We actually spoke in terms of stories and scenarios, full scenarios. I want this, we need this. For the financial system, for this and that, we need these kinds of things. I have this scenario, that scenario. So we have a bunch of different scenarios. And I think these things are just summarizing some of the key points that were made, but we captured on sticky notes, actual verbal scenario, or not verbal, but storyline type scenarios, prosaic type scenarios. So we'll kind of build those things out and put them out there eventually. But it was, it's hard to write all that stuff down in the time that we had, so we just tried to summarize it before. Who's reporting out for the R&D agenda? Should I? Oh, okay, great.
Okay. I think the first challenge was defining what we were talking about. I think that we interpreted our remit as talking about the R&D required in a short term to develop a proposal for kilometer scale modeling and the like, not so much for what is the big proposal that solves everything. I think we started out with what do you need to establish credibility of kilometer scale or any kind of climate model, really. At kilometer scales especially, it's useful to look at short-term forecasts, few days out, this continuity between weather and climate can be capitalized upon in this case. And what you want is a model that's comprehensively good across the range of timescales from weather prediction all the way to climate timescales. It's important to recognize, though, that the weather requirements are very different from climate requirements, or climate requirements are on top of weather requirements. For climate, you want to produce good low clouds over land, over oceans, which don't matter that much for weather, but they're crucial for climate. So I would say the weather requirements are a subset of the climate requirements. The model needs to be coupled to the rest of the Earth system. So you need to represent interactions between atmosphere, ocean, land. On land, that includes the hydrology, the representation of the biosphere, canopies, evapotranspiration, runoff, snow models, and the like. And you want an ocean model that resolves to mesoscale and has good parameterizations of upper ocean turbulence. For example, there's pretty clear evidence that the upper ocean turbulence or upper ocean mixing in the Southern Ocean is important for how the tropical Pacific responds to climate changes. And that's one crucial thing you need to get right. You want seasonal to decadal prediction skill. Seasonal to the extent there is something short-term predictable, and decadal predicting statistics. The seasonal cycle in general, I think, is a good thing to look at and maybe should be emphasized more than we often do. There are large biases in models in simulating the seasonal cycle of sea ice or primary productivity in the biosphere. And those are good targets for model evaluation, model improvement. What you want in the end are accurate simulations of 50 to 100 years lengths or so with good ENSO and low frequency variability statistics that you can get on those timescales. And that again includes a seasonal cycle, and that should be one target for evaluation. You would hope that you get better representation of precipitation, at least deep clouds, extreme events at higher resolution models. We should evaluate those comprehensively. That means evaluate low and higher moments. For precipitation, I think in kilometer scale, the focus is often on the higher moment, but you still have got to get the first moment, the mean values right, and that's where models often fall quite short. This is doing well here is not just a matter of higher resolution, but ultimately we require human resources investment and focus on subgrid scale parameterizations that you continue to lead at any resolution we can achieve in the next few decades for boundary layer clouds, for microphysics, for land processes that are not resolvable, and the like. So to achieve these goals, what do we need? It's getting a little bit more challenging to summarize this. So, I mean, one obvious point is it's challenging to test and calibrate a model if your computational budget allows just 100 years or so of simulation. That's challenging for the atmosphere alone, but even more challenging for coupling to other Earth system components. The hope is that you can develop coupling, testing, predictions on timescales of a few decades. There's an obvious feedback of wildfire on the Earth system through carbon emissions, also more local through aerosol emissions, but on timescales of a few decades, years to decades, it may not be crucial. So wildfire is maybe something you can model in downstream models that you graphed on top of any high resolution climate model, and on top means running offline. Storm surges would be another example, really one of the major sources of economic losses and losses of life. And yet it's probably not something you want to model in a climate model, but predict with downstream models that take, say, a tropical cyclone that a climate model may produce as input, and then predicts what the storm surge is that is associated with the tropical cyclone. So where's the boundary between what's in the model and what's in downstream models? It's hard to say, but as a rule, all the processes that feed back onto the climate system on the timescales you're interested in should be in the climate model. So low cloud biases are clearly important. Low clouds are clearly important for the energy balance over land and ocean. That's clearly something you want to get right in any kind of climate model, kilometer scale or coarser. But then some of these other impacts can be dealt with downscaling and downstream models. Yeah, this is not perfectly organized. So again, the evaluation of models, there was talk about using EarthCare, and NICAM has simulators for various satellite systems that they use. It seems like a great idea and good to capitalize on. Use individual events for evaluating the goodness of a model. And most of that can be done offline with limited data sets and possibly in parallel with the parent simulation to reduce data storage. And again, not perfectly cleaned up, the same point as above there, investment in human resources here, I think is crucial. And I think we shouldn't forget that. We talk a lot about computing, but if you really want to build a great model, you need to invest in the science solidly. And not just coding the model, but developing new concepts for subgrid scale parameterizations. It's important to keep in mind that most subgrid scale parameterizations we use go back to the 1970s and thereafter. That was a great time when many of these things were developed adequate for the data and computational resources at the time. And a lot of them we use rather blindly now, and that's not a rational approach to this problem. We talked about Kelvin's suggestion of having a unified modeling framework. It didn't go very much further than in the first round of discussions. So there is, we all would love to have plug and play compatibility between models all in one framework. And we all have dreamed of that for decades. And we have learned this is difficult to impossible. The obvious thing we can do, and that's already done, I think everyone does it, is the output is reasonably standardized. It makes it easy to evaluate, compare models. And CMIP, I think, has done a great service to the community and forcing a certain standardization there. And I think more standardized tests with standardized input, and we have some of them, EMIP, DCMIP, and the like. These are obvious things we should continue to do. The question about the hardware, so the R&D agenda for the hardware was a bit unclear. To what extent should models be co-designed with the hardware versus use the commodity hardware that's on the market and make the model work on it? We don't have an answer for you. Just one important point came up again. It's important that whatever system is being designed is also useful for building this whole ecosystem that we need downstream to make model output actionable and useful to people. And that means you need to co-locate, compute, and storage, and make the system have components that are well designed for analysis workflows, not just for the brute force computing that we also need. I think that's what it was approximately. So we narrowed the scope, I believe, of what was being asked to this. I think if what you want to know is what you need to really build a great risk assessment tool, the R&D agenda, it's a lot more. And people found this too daunting. So.
Any questions? Please.
So what's the time frame on the R&D relative to timeframes for deploying systems?
You want to answer? I have no idea.
We chose things that could be done in a year or two, I think.
Yeah.
As being the kind of low-hanging fruit that we would want
mean, maybe I can, from my personal point of view, a lot of these things we're talking about here are achievable in an operational model in a timescale of 1 to 2 years if you don't constrain yourself to a kilometer, but say you're good enough with 10-kilometer resolution.
Thanks for revisiting the question of a unified framework. I really, really appreciate that. You know, you never know until yes, but yeah, I mean, plug and play, it's a challenge. It really is. Let's see, I swallowed what I was going to ask. Oh, yeah, so really, really excellent. To what extent would this R&D agenda be enhanced or accelerated by having collaborations that are stronger than they are today? Collaborations are happening clearly among all the different groups, you know, but I think we've heard various people say, yeah, we could be doing better. Is that an important aspect of, like I said, getting to maybe R&D faster, better, whatever? Do you see that as being as being something, if we convey it out of the summit to where it's like, yeah, we want to join forces? In fact, I already heard some folks here say, yeah, we had a conversation and we're going to start working together, you know. So those things are serendipitous sometimes, but is that in your thinking at all, Top? You know, I just was curious.
I think success in this field of climate modeling is increasingly dependent on close collaboration, especially across fields. You need people who are knowledgeable, obviously, in the climate sciences. You need excellent software engineers. You need excellent applied computational mathematicians, and they need to work together and need to work closely together. And the more we can foster that, the more likely we'll succeed. Now, how do you actually do that? I can tell you this from my experience, where I think we have been reasonably successful in building collaborations like that. The more you can co-locate people and have them sit next to each other, the more likely you'll be successful. There is otherwise a tendency for, say, people from outside climate modeling to fly by and say, well, do this, do that, I have this or that tool. And that can be helpful and can incentivize, it can lead to ideation of good things. But often the really good things come about by people sitting together for many hours and working through stuff. And really helps to be in one location. And maybe the other thing to add is, I think what is great about our field, that in general, it's very open. And we have been open with data since the 1950s. I think we have been open with code before open source was a term anyone knew. And I think we are openly collaborating across institutions pretty well. And I think that's great, and obviously something we should continue to do.
Yeah, I think that's spot on. I couldn't agree more. And Jim Hurl reminds me that a lot of things are driven by what people are funded to do, and the timelines of grants and things like that, what agency priorities are and so on, sometimes force people to work in certain areas. And it's increasingly difficult with compliance these days to be able to work on things that you didn't explicitly include in your grant proposal. In fact, it's illegal to do that, which is really unfortunate. We have far less flexibility than we used to, which makes me wonder if there's opportunity with federal agencies to do what you're talking about, Top. I couldn't agree more that they're physically being there, of providing more opportunities for that kind of in-person collaboration, more funding for those kinds of things. And I think that could be very helpful. That's one potential takeaway that we could argue for, that all these great efforts are happening. There's no lack of desire to collaborate, but a lot of times it's funding. And so maybe that's part of a small part of an answer, you know? What do you think?
Let me add one more piece to that. So there's, collaboration, interdisciplinary work is all the rage. And there are private foundations whose agenda it is to foster that. And that's a good idea. But let me just give you one example. There's one foundation, don't need to talk about which one, that has programs, collaborative programs. They're fairly well funded. We were invited to submit a proposal there. I think it would have had a great chance of success. However, they wanted at least 10 PIs on the proposal. And the amount of funding was not like millions per PI, it's like a few 100,000 per PI. And so there's, I think, a fine line to be drawn. You want collaboration, and they should be broad, but you also need to focus and get down to getting stuff done. And if you have too broad a collaboration, that can get very difficult. And so there's a middle ground. You want to be open have active exchange with everyone, but you need to focus to get stuff done.
Right, right, yeah. And there are opportunities out there, as you say, and maybe one thing would be to kind of surface those a little bit more effectively for folks who maybe don't realize they exist or whatever. So yeah, that's really, really great work, guys. Thank you all so much. Any questions for Tapi or the group? Okay, no.
Do you think people want to add? Maria added some notes. You're good, and Chris and okay.
Yeah. Was that a chat GPT thing there?
Yeah, I have two questions, and then one of them is earlier, I think during lunch, I heard that people mentioning about entrepreneur approach. And I'm not sure that somebody can actually elaborate on that, what that actually means. It is actually the source of funding and actually the priority setting and more focus on like the end users and then economic impact and more than scientific curiosity. So that's this is kind of entrepreneur approach. And the second question is, and then in order to actually make this project successful and deliver what we intend to deliver, it's more of an implication on most of the basic science is already in place. And how much basic science and theoretical studies do needed in order to deliver, or it is all there, it's more about implementation.
Maybe the last thing first. So how much basic science do you need? My take is a fair bit, but so one thing you have to recognize that the resources for climate modeling in the US, it's sort of $2 billion a year for everything in climate. It's fairly large. But climate modeling in itself, it's actually quite few people. If you centered at a few centers, and if you just count the people who are really developing climate models, it's relatively few. So I think there is a bit of the field hasn't evolved as quickly as it could for lack of influx of bright young folks working in the area. And I think as a result, we haven't seen the progress you could see that could come from progress in fundamental science. And to me, the most satisfying part of my last few years was actually realizing some of that progress and seeing it's possible. The entrepreneurial approach, what exactly were you thinking about what that would mean?
I'll take a crack at that if you don't mind. I think it came up in the previous breakout session.
Okay.
And I observed as sort of an outsider to this community that it sounds a lot like an academic research community with funding agencies and somewhat zero-sum budgets among a given research area, where the idea that you might concentrate that budget into one large project requires taking pieces of pie out of people's hands, and that's controversial and difficult and hard to imagine. What's potentially on the table with some of the things that Kelvin and Jim were hinting carefully about is infusion of funding and commitment from outside of traditional funding sources. And one might speculate about what those are, but people are saying relatively large. And I think the model that one might draw analogy from would be the Human Genome Project, which was not only government funded, but a virtuous cycle of private and public funding, a race with entrepreneurial innovation and entrepreneurial structures. And so maybe, sorry, I'm from Silicon Valley, there is a huge value to academic discourse and finally grinding and figuring out exactly what the limits of our understanding, our science are. There's also a value to, forgive my naming names, Elon-like full speed ahead, let's get this done as quickly as possible innovation. We might balance those values. My impression of the Human Genome Project is that there were people who were empowered in more executive-like, less committee-like ways to make local decisions for speed of execution of the project and time to solution of the project. And so if it's just this community must change itself, that seems super hard to do in the absence of some major external forcing function, whether it's a crisis or a huge funding opportunity. But if there's maybe both, the climate crisis facing us down and the interest from reinsurance companies and possibly other sorts of philanthropic or other organizations saying, if you scientists believe we could build a system here that could actually provide us with actual feedback, that is worth our putting investment behind, then maybe going slow is worth reconsidering. Maybe you should have people like Eric Lander of the Human Genome Project or various other empowered people. I think I threw Torsten under the bus if he's still here. Maybe you put Torsten in charge of architecture and just have him call the shots about that sub-piece of the project. With that organization, it would of course be riskier. It would be controversial. Would it be more executive execution oriented? And in that sense, entrepreneurial. Like, go fast because the problem is pressing, because we have this opportunity, and offer people the carrot, right? You can continue with your current NSM or NOAA funding and doing the things you want. We're not taking any of that away from you. But there's this new project where if we band together, we can do something great. I think that was part of the promise of the Human Genome Project. I think that got some labs to partially retask their resources. Presumably other biology labs did not necessarily retask, and they were fine doing their previous thing. But the point is to pull. So that was part of the sketch of the entrepreneurial possibility that I was sensing in the room. And so I'm happy to.
That was what we were been talking about. Yeah, exactly. And you said it extremely well, Cliff. Thank you. Very well. Apologize for being from Silicon Valley? Really? Gosh. Please, Doris.
I mean, in the project I'm leading, we're kind of doing that, but you also have to realize what this means, right? We live by quarterly annual milestones. We live by annual funding. People don't know if they're going to be laid off in May or not. And that's part and parcel. I mean, it helps us focus a great deal. But be clear what we're signing up for. So.
No, it's true. As Cliff said, it's a risk, but it's an exciting one, and it's something to think about. I think something to think about. I love the provocative thinking, and again, that we've been saying, you know, and Jim and I, we're not trying to be goofy about this, but we can't tell you what we know, but we can tell you that what we know is true, and you'll hear about it someday. And you'll be like, oh, that's what it was. But it's real. So anyway, it's been an unbelievably good day. And it just reminds me of how extraordinarily talented and thoughtful and dedicated everyone is to what they're doing and to the big picture. And we don't all have to agree. I mean, science never agrees. But the thing is that I love about our community, we all remain friends. This is not like what you see on Capitol Hill. We all remain friends. We all collaborate. We all learn. I've learned a heck of a lot, and I'm still learning. And I'm not the expert here, folks. I'm not a climate scientist. I'm a weather, modeler of fine scale stuff. And I've learned dramatically since I came to Illinois about more climate. And so I'm kind of the Larry Smarr person who or other people I've known who are, trying to make things happen without being the absolute world's expert. I'm very, very far from that. I think you all know. So we wouldn't be having this conversation in other communities. I think we're having it here, which is really fantastic. So just thinking about tomorrow, things are sort of set a little bit because of Zoom and the hotel schedule and food and so on and so forth. So we do need to gather at 8:30 like we've been doing, 7:30 to 8:30. And the planning committee is having dinner again tonight to kind of, think about what we've talked about and so on. We'll probably restructure tomorrow somewhat substantially, I would imagine, and I could envision us being done by noon. I don't not promising you that. We were to be done by 1 o'clock. We might even be done, later in the morning. We will have lunch available to you and so on. But I think we've done a lot of great things. I've written down some stuff that I think I'm going to pitch to the planning committee that we might want to kind of dive more deeply on tomorrow and some of the bigger questions that still remain. But they're not going to take hours and hours of time to discuss. So we'll get back with you. I would just say if you're here fully caffeined up at 8:30, that'll be really good. And we'll just take it from there. Probably spend 2.5 hours, and I can imagine we'd be done by roughly 11. So. Yeah, please go ahead.
Can I still say something since he was throwing me under the bus anyway? But I have a slightly different question. So something for the committee to discuss overnight maybe, and also the attendees. Do we believe it's a research problem or an engineering problem that we are facing? This is a very foundational question because it completely changes your mindset whether to go or not. So to just give you an example, many big companies believe that solving quantum computing, building a quantum computer at this point is an engineering problem, not a research problem. So it has transitioned from trying to figure out how to do it in an abstract way to how to do it in a concrete way. So here I haven't really gotten the gist of the room. So I would like to ask everybody to consider this overnight maybe, and maybe tomorrow morning we run a poll.
Yeah.
Is it a research or an engineering problem to make this happen?
I love it. That's a wonderful question. Absolutely. And to chew on that tonight. And your ideas might change after the second glass of wine. I don't know. But yeah, that's really important. And, yeah, fantastic. And we can take a poll and have a good, robust discussion. And thank you for that. That's marvelous. That's absolutely marvelous. You've obviously made it under the bus and weren't hit by it. So that's good. So, all right. Anything before we adjourn for the day? Any other final comments or Deanne, anything from you? We good? Anybody send us put up the finger in Zoom that they couldn't hear us or something? No, I think we're good. Okay. Yeah. We might want to focus our R&D on telecommunication and video conferencing. That's an important agenda. So, okay, well, fantastic. We're straight up 5 o'clock. Thank you all again. So just be here 7:30 breakfast, if you call it that. We didn't have, I know Jim wanted sausage and fried okra and eggs and, but this is an NSF grant and they cut the budget in half already. So, but anyway, have a great evening. Enjoy, and we'll see you here tomorrow morning. Thank you.